Wormholes. The mysterious shortcuts through space and time that have fascinated scientists, science fiction writers and dreamers alike. But do they really exist? In this video, we're going to dive deep into the science, the theories, and the possibilities that surround these cosmic tunnels. The concept of a wormhole was first introduced through the equations of general relativity, thanks to none other than Albert Einstein. But what exactly is a wormhole? Simply put, it's a hypothetical bridge connecting two distant points in spacetime, allowing for incredibly fast travel across vast distances of the universe. The idea sounds like something straight out of science fiction, and in many ways it is. Movies like Interstellar and TV shows like Star Trek have popularized wormholes as a way to cross the universe in a matter of moments. But could these theoretical shortcuts actually exist in the real world? At the heart of the wormhole theory is Einstein's theory of general relativity. This theory tells us that massive objects like stars and planets can bend the fabric of space and time. A wormhole is essentially a tunnel through this warped space, potentially allowing you to travel from one side of the universe to the other in no time at all. Of course, these wormholes wouldn't be easy to create, even if they do exist. They require exotic forms of matter that we've never observed in nature. This type of matter, often called negative energy, would be necessary to keep a wormhole open. Without it, the tunnel would collapse, sealing off the shortcut. Wormholes come in different shapes and forms. There are Schwarzschild wormholes, also known as Einstein-Rosen bridges, which are based on black holes. And then, there are traversable wormholes, which could, in theory, allow for travel between distant parts of the universe, or even through time itself. The key difference? Traversable wormholes wouldn't have the deadly gravitational forces that black holes do. One of the most intriguing aspects of wormholes is their connection to time travel. If you could travel through a wormhole, you might be able to arrive at your destination before you even left. This opens the door to all kinds of time paradoxes and raises huge questions about the nature of causality in the universe. But before we get too carried away with time machines and intergalactic travel, it's important to remember that we have yet to observe a wormhole. All of this is still purely theoretical, and many physicists argue that even if wormholes do exist, they might not be stable enough for any practical use. Still, the potential of wormholes is enough to keep scientists and researchers fascinated. The idea of using these cosmic shortcuts to travel to distant galaxies or even different dimensions is one of the most exciting possibilities in modern physics. And who knows? With advances in technology, we might someday find a way to explore these mysterious tunnels. In this video, we'll break down everything you need to know about wormholes, from their theoretical foundations to their potential existence, and even their possible role in the future of space exploration. A wormhole is essentially a tunnel connecting two separate points in space-time. Imagine bending a piece of paper so that two distant points touch each other. That's how a wormhole works, folding space to bring faraway places close. In more scientific terms, wormholes are solutions to the equations of general relativity, offering a shortcut through the universe. These theoretical structures could link regions of space separated by billions of light years, or even different universes entirely. One of the key aspects of a wormhole is that it acts as a bridge, potentially allowing matter or information to travel through it. This concept has led to fascinating discussions about faster-than-light travel and instant communication across the cosmos. Wormholes can be thought of as tunnels with two ends, each located at a different point in space or time. They might connect not only two distant places, but also two moments in time, making them central to theories about time travel. The two ends of a wormhole are often referred to as mouths. The region inside the wormhole is called the throat, and it's through this throat that travelers would pass. Theoretically, moving faster than light can travel across normal space. However, not all wormholes are the same. Some types, like the Schwarzschild wormhole, are purely theoretical and would collapse before anything could pass through them. These are non-traversable and exist only as a mathematical curiosity. Traversable wormholes, on the other hand, could, in theory, allow safe passage from one end to the other. These wormholes would require exotic matter to keep their throats open, preventing collapse and allowing something or someone to move through them. The possibility of a traversable wormhole is one of the most exciting ideas in theoretical physics. If such a structure could exist, It might revolutionize how we think about space travel, potentially allowing us to travel vast distances in a fraction of the time. Despite the intrigue, there's a catch. The idea of a traversable wormhole hinges on the existence of negative energy or exotic matter, substances we've yet to observe in nature. This raises questions about whether wormholes could ever exist outside of theory. In classical physics, wormholes seem impossible because of their instability. Any disturbance might cause them to collapse, making travel through them highly unlikely. However, quantum theory opens new possibilities for stabilizing these tunnels. Wormholes also defy our intuitive understanding of space and distance. While 2 points may seem far apart in normal space, the presence of a wormhole could make them appear much closer, a concept that challenges our everyday experience of the universe. Physicists have used wormhole models to explore questions about the fundamental nature of reality. These theoretical bridges allow us to consider what the universe would look like if space and time could be manipulated in ways we can't yet fully comprehend. Interestingly, wormholes are often tied to the idea of alternate dimensions or parallel universes. Some theories suggest that a wormhole could serve as a gateway between not only different locations, but entirely different realities. Wormholes aren't just a tool for sci-fi plots. They have deep implications for understanding the universe. If they exist, they could provide answers to some of the biggest mysteries in physics, from the nature of space-time to the possibility of multiverses. Even though wormholes remain a theoretical concept, the mathematical foundation behind them is solid. As our understanding of physics evolves, especially in areas like quantum gravity, the possibility of wormholes could shift from theoretical curiosity to scientific reality. There are two main types of wormholes that have captured the attention of scientists: Schwarzschild wormholes and traversable wormholes. These two types represent vastly different possibilities for how wormholes might function in the universe. Schwarzschild wormholes, also known as Einstein-Rosen bridges, are based on solutions to Einstein's field equations. These theoretical wormholes are linked to black holes and exist only as a mathematical concept rather than something we could use in reality. The problem with Schwarzschild wormholes is that they are unstable. The moment something tries to pass through, they collapse, cutting off the connection between two regions of space. Essentially, they are non-traversable. Because they collapse too quickly, Schwarzschild wormholes are often seen as a theoretical curiosity rather than a practical way to travel through space. They serve as an interesting solution in general relativity but don't offer any practical means for interstellar travel. Traversable wormholes, on the other hand, are where things get more exciting. These are hypothetical wormholes that could, in theory, allow safe travel from one point in the universe to another, without collapsing under their own gravitational forces. The idea behind a traversable wormhole is that it remains open and stable long enough for matter to pass through. Unlike Schwarzschild wormholes, these structures would not pinch off or implode before anything could get through. For a wormhole to be traversable, it would require a form of matter that we haven't yet discovered: exotic matter. This exotic matter would have negative energy density, which could keep the wormhole's throat open, allowing something to pass from one end to the other. The exotic matter needed for a traversable wormhole is purely theoretical at this point. We've never observed anything like it, but its existence is key to making a wormhole stable enough for practical use. While traversable wormholes are purely speculative, they've inspired a lot of research in theoretical physics. If they could be created, they would fundamentally change our understanding of travel and time, offering shortcuts through space. The concept of a traversable wormhole isn't limited to just space travel. Some theories suggest they could also be used for time travel, potentially connecting different moments in time as well as different regions of space. In theory, traversable wormholes could allow someone to travel vast distances in a fraction of the time it would normally take. They could link two distant parts of the universe, bypassing the need to travel through normal space. However, even if a traversable wormhole were discovered, the challenge of actually using it would be enormous. We don't yet have the technology or even the understanding to manipulate space-time in the ways these wormholes would require. Scientists continue to explore these ideas, testing the limits of what's possible within the framework of general relativity and quantum theory. The potential of traversable wormholes remains one of the most tantalizing mysteries in modern physics. If we ever did find a traversable wormhole, It might revolutionize everything we know about space exploration. Instead of taking centuries to reach other galaxies, we might be able to make the journey in moments, opening up the universe like never before. While Schwarzschild wormholes might not be useful for travel, traversable wormholes remain a captivating possibility. They push the boundaries of our current scientific understanding, challenging us to think beyond the limits of our technology and knowledge. The mathematical foundation for wormholes comes directly from Einstein's field equations in general relativity. These equations describe how mass and energy warp the fabric of spacetime, which in turn leads to the theoretical possibility of a wormhole. In essence, a wormhole is a solution to these equations, where spacetime is curved in such a way that two distant points become connected through a tunnel-like structure. It's this curvature that allows the concept of a shortcut across space to emerge. The geometry of a wormhole is defined using what physicists call a metric, a way of measuring distances in curved spacetime. The most famous example is the Schwarzschild metric, which also describes black holes. The mathematics suggest that under certain conditions, spacetime can bend enough to form a tunnel. But this doesn't mean the wormhole is traversable. For that, additional factors like exotic matter are required to stabilize it. The throat of a wormhole, mathematically, is where the curvature of spacetime becomes extreme. This is the narrow passage that connects the two ends of the wormhole, theoretically allowing for travel between them. The stability of a wormhole is a major mathematical challenge. Without exotic matter, any attempt to travel through the wormhole would cause it to collapse immediately, making the journey impossible. To prevent collapse, theoretical models require negative energy, something that doesn't naturally occur in large amounts. This negative energy would counteract the gravitational forces that would otherwise close the wormhole. Quantum mechanics also plays a role in the mathematics of wormholes. Some theories suggest that tiny microscopic wormholes could exist at the quantum level, though these would be far too small for any practical use. One of the most famous equations connected to wormholes is the Einstein-Rosen bridge, which describes a non-traversable wormhole. This solution shows how a black hole could theoretically be connected to another part of spacetime. The Einstein-Rosen bridge is mathematically elegant but physically impractical for travel. The key problem is that the bridge would collapse too quickly for anything to pass through it, making it a one-way trip to nowhere. In contrast, the Morris-Thorne solution is a mathematical model of a traversable wormhole. This model introduces the idea of exotic matter as a stabilizing force, offering a theoretical pathway for safe passage through the wormhole. The mathematics also reveals that the ends of a wormhole, called mouths, don't necessarily have to be in the same region of space or time. This opens up the possibility of wormholes acting as time machines, connecting different moments in history. Mathematically speaking, wormholes could connect not only distant parts of our universe, but also different universes entirely. This is where the idea of parallel universes and alternate realities comes into play, though it remains speculative. Einstein's theory of general relativity provides the framework for understanding how wormholes could exist, but it's the marriage of relativity with quantum theory that might hold the key to making sense of these complex structures. The equations that describe wormholes are beautiful, but incredibly complex. They represent one of the most fascinating intersections of mathematics and theoretical physics, offering a glimpse into the deeper workings of the universe. The Einstein-Rosen bridge is one of the earliest and most famous theoretical models of a wormhole. It was proposed by Albert Einstein and Nathan Rosen in 1935 as a solution to the equations of general relativity. This bridge connects two distant points in spacetime through a tunnel-like structure. In simple terms, the Einstein-Rosen bridge is a mathematical description of a wormhole that forms between two black holes. It suggests that if you fall into one black hole, you might emerge from another point in space, though the reality is far more complicated. The bridge is created by the intense gravitational forces of a black hole. As spacetime bends and twists under these forces, the bridge theoretically forms, linking two otherwise separate areas of the universe. But it's not as simple as jumping in and traveling through. One of the major issues with the Einstein-Rosen bridge is that it's not stable. The bridge collapses too quickly for anything, including light, to pass through it. This makes it an intriguing mathematical concept, but not something that could be used for travel. In the context of black holes, the Einstein-Rosen bridge helps explain some of the stranger aspects of how black holes might connect to other parts of space. But since no material could survive the journey, it's more of a theoretical tool than a practical one. The collapsing nature of the bridge is due to its connection with black holes. As you approach the event horizon of a black hole, time slows down and space compresses, making it impossible to cross the bridge before it pinches off. Physicists realized early on that the Einstein-Rosen bridge, while fascinating, doesn't offer a traversable wormhole. It's a mathematical artifact of general relativity, showing that spacetime can be linked in unexpected ways, even if those ways aren't usable. Another interesting aspect of the Einstein-Rosen bridge is that it's symmetrical. Each end of the wormhole looks the same, which means both ends would behave like black holes. However, nothing could ever come back out, reinforcing the one-way nature of the bridge. Despite its limitations, the Einstein-Rosen bridge laid the groundwork for further research into wormholes. It showed that spacetime can theoretically be connected in ways that defy our everyday understanding, even if these connections are short-lived. The concept also introduced the idea that wormholes could link two different universes. If one end of the bridge leads to a different universe, it raises the possibility that black holes could be gateways to other realms, though we have no evidence for this. While the Einstein-Rosen bridge is often associated with wormholes in popular culture, its role is more symbolic in scientific discussions. It represents the potential for space-time to fold in on itself and form connections that are otherwise impossible to visualize. Over time, physicists moved beyond the Einstein-Rosen bridge to explore models of wormholes that could theoretically stay open. The idea of traversable wormholes emerged from the desire to overcome the limitations of the collapsing Einstein-Rosen bridge. Still, the bridge remains an important milestone in our understanding of space-time. It's one of the earliest hints that our universe might have deeper connections hidden within its structure, even if we can't access them. Einstein and Rosen likely had no idea their bridge would inspire generations of physicists to explore the concept of wormholes further. Though their original model was impractical for travel, it sparked curiosity about the nature of space, time, and black holes. Today, the Einstein-Rosen bridge is a key piece of the puzzle in understanding how wormholes might work, even if it's not the ultimate solution. It's a testament to the power of theoretical physics to reveal hidden possibilities in the fabric of the cosmos. Wormholes are deeply rooted in the framework of general relativity. Einstein's theory describes how massive objects bend the fabric of space-time, creating gravitational effects that we experience as gravity. This same bending of space-time is what allows for the possibility of wormholes. In general relativity, gravity is not seen as a force, but as a curvature of space and time. When a massive object, like a planet or a star, distorts space-time, it creates pathways that other objects follow, much like marbles rolling along a curved surface. Wormholes, in theory, are extreme examples of this curvature. A wormhole, mathematically, can be viewed as a tunnel connecting two regions of space-time. The idea stems from how general relativity allows for the possibility that space can fold over itself, creating a bridge between distant points, even if those points are billions of light-years apart. Einstein's equations show that if space-time can be warped enough, a shortcut between distant locations could form. The key lies in understanding that space-time isn't flat. It's a dynamic, flexible entity shaped by mass and energy. These equations suggest that wormholes could form in areas of intense gravitational fields. Black holes, which represent some of the most extreme warping of space-time, offer one possible environment where these connections could theoretically exist. General relativity provides the blueprint for how space and time behave on a cosmic scale. While it doesn't directly predict wormholes, it leaves open the possibility that such structures could exist under the right conditions. In this sense, wormholes are a natural extension of Einstein's work. The concept of a wormhole emerges from the solutions to Einstein's field equations. Specifically, the Einstein-Rosen bridge is one such solution, demonstrating that space-time can connect two points through a black hole. However, this bridge collapses too quickly for anything to pass through. To keep a wormhole open, the equation suggests something extraordinary is needed: exotic matter with negative energy. Without this, the intense gravitational forces would cause the wormhole to pinch off, making travel through it impossible. The connection between general relativity and wormholes is not just theoretical. Some physicists believe that if we discover exotic matter or learn more about quantum gravity, we might find evidence that wormholes could exist. But for now, they remain purely mathematical constructs. In the context of general relativity, wormholes also represent a solution to the challenge of traveling faster than light. Since the theory prohibits faster than light travel through space, wormholes could theoretically provide a loophole by allowing objects to take a shortcut through space-time itself. General relativity's description of space-time as a flexible, dynamic medium is essential for understanding how wormholes could work. Without this understanding of curved space-time, the concept of a wormhole wouldn't be possible. Even though general relativity suggests that wormholes could exist, the theory doesn't guarantee their stability. It simply shows that under certain extreme conditions, space-time might bend in such a way that a wormhole could form, if only briefly. The limitations of general relativity become clear when we try to apply it to extremely small scales, such as those found inside wormholes. This is where quantum mechanics enters the picture, offering potential insights into the nature of these connections. Despite its limitations, general relativity remains the best framework we have for understanding how wormholes could theoretically function. The theory gives us a glimpse into the possibility of connecting different regions of space, even though we're far from proving such structures exist. Wormholes are a fascinating consequence of general relativity's equations, showing just how strange and complex our universe might be. They challenge our understanding of space, time, and the very nature of reality itself. Einstein's theory of relativity fundamentally changed our understanding of space, time, and gravity. It's divided into two parts, special relativity and general relativity, each addressing different aspects of how the universe works at high speeds and large scales. Special relativity, introduced in 1905, focuses on objects moving at constant speeds, particularly near the speed of light. It introduced the idea that time and space are relative, meaning they change depending on how fast you're moving compared to another observer. One of the most famous outcomes of special relativity is the equation E=mc2, which shows that energy and mass are interchangeable. This principle has vast implications for how we understand energy, nuclear power, and even the potential for traveling close to light speed. General relativity, developed a decade later in 1915, expands on these ideas by incorporating gravity into the picture. Instead of viewing gravity as a force between two objects, Einstein described it as the result of the curvature of space and time. Massive objects like stars or planets warp the space-time around them. This curvature is what we experience as gravity. It's why planets orbit the sun, or why objects fall toward the Earth. The closer you are to a massive object, the more time itself is affected. Time actually moves slower in stronger gravitational fields, an effect known as time dilation. This idea became central to understanding not only gravity, but also how time behaves in extreme conditions. General relativity's equations also describe how light bends when it passes near a massive object. This bending of light, known as gravitational lensing, has been observed in distant galaxies, proving Einstein's predictions with remarkable accuracy. Einstein's theory of relativity goes beyond just explaining the motion of planets and stars. It allows us to explore the fundamental structure of space-time itself. It's within this framework that the concept of wormholes becomes possible. Relativity shows that space and time are not separate entities. They are intertwined in a four-dimensional fabric called space-time. When this fabric is bent or stretched, it opens the door to phenomena like black holes and, theoretically, wormholes. Without Einstein's theory, we wouldn't have a foundation for understanding how extreme gravitational forces could create the conditions for a wormhole. His work laid the groundwork for all modern physics that deals with the large-scale structure of the universe. Time travel, another concept often associated with wormholes, also stems from relativity. Einstein showed that time isn't a constant. It can stretch or compress depending on speed and gravity. These distortions of time are critical to the possibility of using wormholes for time travel. Relativity also introduces the idea of the cosmic speed limit. Nothing can travel faster than the speed of light. This limitation means that traveling across vast distances in space would take enormous amounts of time, which is why wormholes become such an attractive solution. The theory of relativity has been confirmed by countless experiments, from observing the orbit of Mercury to the detection of gravitational waves. These findings not only validate Einstein's ideas, but also encourage further exploration into the more exotic possibilities his equations suggest. Einstein's insights reshape the way we understand the universe, moving us beyond Newtonian physics and into a world where space and time are flexible, dynamic, and interconnected. These concepts remain central to modern astrophysics and cosmology. Without relativity, the very idea of bending space-time to create shortcuts like wormholes wouldn't exist. Einstein's theory gave us the mathematical tools to imagine how the universe might allow such extraordinary phenomena to occur. The curvature of space-time is central to understanding how gravity works in Einstein's theory of general relativity. Rather than thinking of space as flat and empty, it's more like a flexible fabric that can be warped by the presence of mass and energy. Massive objects like stars and planets create dips or bends in this fabric. Smaller objects, such as moons or spacecraft, follow the curves created by these dips, which is what we experience as the force of gravity pulling objects toward each other. This curvature explains why planets orbit the Sun. The Sun's immense mass warps space-time around it, creating a kind of valley that the planets roll along, keeping them in orbit without any force pulling them in a straight line. The greater the mass of an object, the more sharply it bends space-time. For instance, a black hole bends space-time so dramatically that not even light can escape its pull, creating what we call an event horizon. This warping of space-time doesn't just affect the paths of objects. It also influences the flow of time itself. Time moves more slowly in regions of space where gravity is strongest, an effect called gravitational time dilation. You can think of space-time curvature as creating a kind of invisible structure, guiding how everything in the universe moves and behaves. The more curved space-time is in a particular area, the stronger the gravitational effects we observe. Einstein's equations describe exactly how space-time bends in response to mass and energy. This bending, in turn, tells objects how to move, leading to the paths we see planets, stars, and galaxies follow across the cosmos. This curvature isn't just theoretical, it's been observed. One famous example is the bending of starlight by the Sun during a solar eclipse, which was one of the first confirmations of Einstein's predictions about space-time. Space-time curvature also helps explain how objects in the universe can influence each other even across vast distances. Every object with mass contributes to the overall shape of space-time, affecting the motion of everything around it. In the context of wormholes, the idea is that space-time can be bent so extremely that two distant points touch, creating a shortcut. The curvature would be so intense that, instead of following the normal rules of space, you could move directly from one point to another through a wormhole. The degree of space-time curvature determines how extreme the gravitational effects will be. In regions like the edge of a black hole, the curvature becomes almost infinite, creating singularities where our current understanding of physics breaks down. Space-time isn't static. It can change and evolve over time. The movement of massive objects, such as merging black holes, can cause ripples in space-time known as gravitational waves. These waves are real distortions in the fabric of the universe, spreading out from cosmic events. Curvature can also be affected by energy, not just mass. Dark energy, the mysterious force accelerating the expansion of the universe, could be altering the shape of space-time on a grand scale, though we don't yet fully understand how. This flexibility of space-time is what allows for the theoretical existence of wormholes. If space-time can be curved, stretched, and even connected in extreme ways, the idea of forming tunnels through it, like wormholes, becomes mathematically possible. The concept of curved space-time challenges our intuition, but it's been consistently verified through experiments and observations. It's the underlying framework that lets us explore phenomena like black holes, gravitational waves, and potentially wormholes. Einstein's field equations are the core of general relativity, describing how matter and energy influence the curvature of space-time. These equations are a set of 10 interrelated differential equations, linking the distribution of matter to the geometry of the universe. The solutions to these equations reveal the structure of space-time under various conditions. For instance, they can describe the space-time around stars, planets, and black holes, as well as more exotic objects like wormholes. Now, one of the most famous solutions is the Schwarzschild solution, which describes the space-time surrounding a non-rotating spherical mass, such as a simple black hole. This solution shows how massive objects warp the space around them, creating gravitational fields. Another key solution is the Kerr metric, which applies to rotating black holes. This solution predicts that rotating black holes create a swirling effect in spacetime, dragging it around with them, an effect known as frame dragging. And these solutions help explain different types of black holes, neutron stars, and other dense cosmic objects. They also pave the way for exploring more speculative solutions, such as wormholes, which represent extreme curvatures of spacetime. The Einstein-Rosen bridge is one such solution, describing a type of wormhole that connects two black holes. Although it collapses too quickly to allow travel, it provides a mathematical foundation for understanding how spacetime could connect distant regions. Other solutions, like those proposed by Morris and Thorne, involve traversable wormholes, which could theoretically allow objects to pass from one part of the universe to another. These solutions require the presence of exotic matter to keep the wormhole open. Each solution to Einstein's field equations presents a different possibility for how spacetime behaves under extreme conditions. Some predict stable structures like stars and planets, while others suggest the existence of highly unstable or hypothetical phenomena. Finding a solution to the field equations is a complex mathematical task, often requiring simplifications or assumptions. For example, assuming a perfectly spherical object or ignoring rotation can make the equations easier to solve, but may not capture all the details of real-world objects. Despite the difficulty of solving them, these equations have provided accurate predictions for a wide range of cosmic phenomena. From predicting the orbit of Mercury to the bending of light around massive objects, the solutions offer powerful insights into the universe. Some solutions to Einstein's equations suggest that the universe could contain regions where time behaves very differently. These regions might allow for time dilation, where time moves slower in stronger gravitational fields, or even time travel through certain types of wormholes. The possibility of wormholes comes directly from the flexibility of Einstein's equations. They show that spacetime can be manipulated, potentially creating shortcuts or tunnels, but only under very specific and extreme conditions. Even though many solutions to the field equations describe stable, well-understood objects, the more exotic solutions challenge our understanding of reality. Wormholes, singularities, and even the possibility of parallel universes are all theoretical possibilities rooted in these equations. The solutions provide a mathematical playground where physicists can test the boundaries of space and time. They allow us to explore ideas like faster-than-light travel and alternate dimensions, even if these remain speculative for now. Ultimately, the field equations are a tool for mapping out how space-time interacts with everything in the universe. Whether describing something as familiar as Earth's gravity or something as strange as a wormhole, they give us a deeper understanding of the cosmos. Exotic matter is one of the key ingredients required to make traversable wormholes possible. It refers to a hypothetical form of matter that possesses negative energy density, something not yet observed in nature. This exotic matter would be necessary to keep a wormhole's throat open, preventing it from collapsing under gravitational forces. Negative energy, unlike the positive energy we're familiar with, would exert a repulsive gravitational force. This force would counteract the intense gravitational pull that would otherwise pinch off a wormhole, making travel through it impossible. In theory, the existence of exotic matter with negative energy could stabilize a wormhole, allowing it to remain open long enough for matter or even people to pass through. Without it, the wormhole would close too quickly, rendering it non-traversable. Scientists speculate that exotic matter might be linked to certain quantum effects, such as the Casimir effect. This phenomenon, observed in laboratory conditions, involves the creation of a tiny amount of negative energy between two closely spaced plates, hinting that negative energy might exist on microscopic scales. However, the negative energy produced by the Casimir effect is incredibly small, nowhere near enough to stabilize a macroscopic wormhole. It raises the possibility that exotic matter might exist, but harnessing it for practical use is far beyond our current technological abilities. The concept of negative energy also ties into quantum theory, which suggests that vacuum energy fluctuations might briefly produce exotic particles with negative energy. These particles could potentially play a role in keeping a wormhole open, but this remains highly speculative. For a traversable wormhole, the amount of exotic matter required would be enormous. It would need to generate a gravitational repulsion strong enough to counterbalance the natural tendency of spacetime to collapse under its own weight. Despite the challenges, the idea of exotic matter and negative energy remains crucial to the discussion of wormholes. Without some kind of negative energy to keep a wormhole stable, the theoretical possibility of using these structures for travel seems nearly impossible. Negative energy and exotic matter are also central to the idea of faster-than-light travel. If space-time could be manipulated using negative energy, it might allow for shortcuts through the universe, bypassing the speed of light limit imposed by relativity. The search for exotic matter extends beyond just wormhole physics. It also has implications for other areas of theoretical physics, such as the study of dark energy and the expanding universe. Some scientists wonder if dark energy itself might be a form of exotic matter on a cosmic scale. There's no direct evidence for the existence of exotic matter, but it remains a fascinating area of research. It challenges our understanding of what's possible in the universe and pushes the boundaries of both classical and quantum physics. Wormholes have long been thought of as potential gateways for time travel. If a wormhole could connect not just 2 points in space, but 2 different moments in time, it would open up the possibility of moving backward or forward in time. The idea stems from the way space-time is curved and linked in general relativity. In theory, one end of a wormhole could be placed near a strong gravitational field, like a black hole, where time moves more slowly due to gravitational time dilation. The other end could remain in a region of weaker gravity, creating a time difference between the two. By traveling through the wormhole, you could arrive at the weaker gravity side before the time you left. This would allow you to effectively step into the past or future, depending on how the wormhole is configured and the time dilation involved. The idea is fascinating but comes with significant complications. For one, wormholes that allow time travel might be highly unstable, making the trip dangerous or impossible. The exotic matter required to keep such a wormhole open adds another layer of difficulty. There are also concerns about time travel paradoxes, such as the famous grandfather paradox. If someone were to travel back in time and change an event, like preventing their grandparents from meeting, it raises the question of how their future self could exist to make the trip in the first place. Physicists have proposed several possible resolutions to these paradoxes, including the idea that time travel through a wormhole might create a branching timeline. Instead of changing the past, a traveler would simply create a new alternate timeline that doesn't affect their original one. Others suggest that the universe might have built-in safeguards against these kinds of paradoxes. For example, the Novikov self-consistency principle suggests that any action taken by a time traveler would be consistent with history, preventing paradoxes from occurring. Still, the practical challenges of using wormholes for time travel are immense. Even if a traversable wormhole could be created, controlling how and when it connects different points in time remains purely theoretical. The laws of quantum physics and relativity would need to work together in ways we don't fully understand yet. Additionally, time travel through wormholes might only be possible in a very limited sense. It could be that only certain kinds of time loops are allowed, or that the amount of time you can travel through is constrained by the size and stability of the wormhole. Wormholes themselves are hypothetical, and the idea of using them for time travel pushes the boundaries of current scientific knowledge. While they offer a tantalizing glimpse at what might be possible, we don't yet have the technology or understanding to test these ideas. If time travel through wormholes were ever proven possible, it would fundamentally change our understanding of cause and effect. It would force us to rethink how events are linked across time and space, and how we interact with both the past and the future. Some physicists speculate that if advanced civilizations exist elsewhere in the universe, they might have already discovered how to manipulate wormholes for time travel. This raises the question of whether we would ever encounter travelers from our own future or other parts of the universe. However, time travel might also be limited by natural laws that we don't fully comprehend. There could be constraints, hidden within the fabric of space-time, that prevent backward travel or limit how far into the future one could go. For now, time travel through wormholes remains a highly speculative area of study. The theoretical groundwork exists, but many pieces of the puzzle are still missing. It's an area that bridges the gap between science fiction and the very edges of modern physics. If the mysteries of time travel through wormholes are ever unlocked, they could open up entirely new realms of exploration. But for now, they remain among the greatest mysteries of space and time, waiting for deeper insights into the nature of the universe. A closed timelike curve is a concept in general relativity that describes a loop in spacetime, where an object could theoretically return to its own past. This kind of loop would allow time travel in a way that seems paradoxical, as it lets the future affect the past. The idea of a closed timelike curve arises from solutions to Einstein's equations, particularly in scenarios involving intense gravitational fields. These curves suggest that spacetime can fold back on itself, creating a pathway that loops through time. If you were to follow a closed timelike curve, you could move forward in time and eventually end up back at the moment you started. In essence, you'd be traveling through time in a circular fashion, continuously looping between the past and the future. Closed timelike curves have been a topic of debate among physicists. While they are mathematically valid within the framework of general relativity, their existence would lead to puzzling paradoxes, such as the possibility of interacting with your past self. One of the most intriguing aspects of closed timelike curves is their connection to wormholes. Some theories suggest that wormholes could create these loops in spacetime, allowing for backward time travel through the curve. However, the existence of closed timelike curves could also violate causality, the idea that cause and effect must follow a linear sequence. This raises deep questions about the nature of time and whether our universe would permit such loops to exist. Physicists have proposed different ways that closed timelike curves might behave. Some suggest that they could exist in a way that avoids paradoxes, while others believe that fundamental laws of the universe might prevent them from forming at all. The Novikov self-consistency principle is one attempt to resolve these paradoxes. It states that any actions taken within a closed timelike curve would be consistent with the established timeline, preventing changes to the past and avoiding contradictions. In this view, you might be able to travel back in time, but you wouldn't be able to change anything that would create a paradox. Your actions would always be part of the original sequence of events, ensuring that the timeline remains stable. Still, the practical reality of closed timelike curves is far from certain. Even though they appear in theoretical solutions to Einstein's equations, there is no experimental evidence that such loops exist in our universe. If closed timelike curves do exist, they would likely require extreme conditions, such as those near black holes or within hypothetical structures like rotating cosmic strings. These exotic environments might allow spacetime to twist in ways that form these loops. There are also concerns about the stability of closed timelike curves. Just as wormholes need exotic matter to remain open, these curves might require forms of energy or matter that we haven't yet discovered to function without collapsing. Some physicists believe that quantum mechanics might play a role in preventing closed timelike curves from causing paradoxes. Quantum uncertainty could introduce a level of unpredictability that makes the loops consistent with the rest of the universe. Others suggest that the presence of a closed timelike curve would cause the universe to self-correct in some way, preventing any significant disruptions to the flow of time. In this scenario, the laws of physics might contain hidden mechanisms that safeguard causality. Despite the fascinating possibilities, closed timelike curves remain speculative and highly controversial. They challenge our understanding of time, causality, and the structure of space-time itself, pushing the boundaries of both physics and philosophy. Whether they represent a real aspect of our universe or merely a mathematical curiosity, closed timelike curves continue to spark debate and inspire new ways of thinking about the nature of time travel. Time travel paradoxes are one of the biggest challenges to the idea of traveling through time. They arise because time travel seems to break the basic laws of cause and effect, leading to contradictions that are difficult to resolve. These paradoxes force us to question how events unfold and whether changing the past is even possible. The most famous of these paradoxes is the grandfather paradox. In this scenario, a time traveler goes back in time and prevents their grandfather from meeting their grandmother. This action would mean the time traveler is never born, but if they were never born, how could they have traveled back in time in the first place? Another well-known paradox is the predestination paradox, where events in the past are caused by a time traveler trying to change them. In this case, attempts to alter the timeline actually become part of the timeline itself, meaning that the time traveler's actions were always meant to happen. The bootstrap paradox takes this even further. It involves an object or information sent back in time that has no clear origin. For example, Imagine a scientist from the future sends the design for a time machine back to their past self. The question becomes, who actually invented the time machine if it existed in both timelines? These paradoxes make time travel seem almost impossible, without breaking the rules of causality. If cause and effect are out of order, it's hard to understand how events can logically connect, which has led many scientists to believe that time travel might be fundamentally forbidden by the laws of physics. One possible solution is the idea of alternate timelines or parallel universes. Instead of creating paradoxes by changing the past, time travelers might create a new, alternate version of history. In this model, changes to the past wouldn't affect the original timeline, but would lead to a branching reality. This idea, sometimes called the many worlds interpretation, suggests that each action a time traveler takes might split the universe into multiple parallel timelines. Each timeline would evolve independently, with no impact on the original one, thus avoiding paradoxes. Another theoretical solution is the Novikov self-consistency principle. According to this principle, any action taken by a time traveler must be consistent with the history that already exists. In other words, the timeline is fixed, and no matter what the traveler does, they cannot change the past in a way that leads to a contradiction. The self-consistency principle allows for time travel without the danger of paradoxes. Any event that happens was always meant to happen, meaning that a time traveler could go back in time, but would be unable to change the course of history in any meaningful way. Despite these theoretical solutions, time travel paradoxes remain one of the most intriguing problems in modern physics. They highlight the tension between the laws of classical physics and the more flexible nature of quantum mechanics, which might hold the key to understanding time travel. Quantum mechanics introduces uncertainty into the picture, and some physicists believe that this uncertainty could smooth out the contradictions caused by time travel. In the quantum world, outcomes aren't fixed, so paradoxes may be less likely to occur. Time travel paradoxes also raise deep philosophical questions about free will and determinism. If time travelers are bound by self-consistency or alternate timelines, do they have any real control over their actions? Or are they simply playing out a predetermined role in a fixed timeline? The paradoxes force us to think about the nature of time itself. Is time something that flows in one direction, or is it a more fluid construct that can be bent, looped, or even reversed under the right conditions? The answers to these questions are still unknown. Some scientists believe that the very presence of time travel paradoxes might be a sign that time travel to the past is impossible. The contradictions they create could act as a natural barrier, preventing any backward time travel from occurring in our universe. Others see these paradoxes as challenges to be solved. If we can understand the mechanisms that cause them, we might discover entirely new principles of physics that allow time travel without breaking the fundamental rules of the universe. For now, time travel paradoxes remain a thought experiment, a way to explore the limits of what we know about time, causality, and the universe. They may never have a practical resolution, but they continue to push the boundaries of scientific inquiry. Many famous physicists have weighed in on the possibility of using wormholes for time travel. Stephen Hawking, for instance, was skeptical of time travel through wormholes. He proposed what is known as the chronology protection conjecture, suggesting that the laws of physics might prevent time travel to avoid paradoxes. Hawking believed that even if a wormhole could allow travel to the past, something would likely happen to close it before paradoxes could arise. He argued that nature might have built in safeguards to preserve the integrity of causality and prevent time loops from forming. Kip Thorne, on the other hand, has been more open to the possibility of time travel through wormholes. He helped popularize the idea of traversable wormholes in the 1980s, and even consulted on the film Interstellar, where a wormhole was used for interstellar travel. Thorne explored the mathematics behind time travel, but acknowledged the enormous challenges in creating and maintaining a wormhole. Carl Sagan, while writing his novel Contact, asked Kip Thorne to help him develop a scientifically plausible method for faster-than-light travel. This collaboration between Sagan and Thorne led to the idea of a traversable wormhole as a scientifically grounded concept, even though time travel was only a side effect of the discussion. Michio Kaku has also explored the idea of time travel through wormholes in his work on theoretical physics. He believes that while wormholes might exist, creating one large enough for humans to travel through would require technology far beyond anything we have today, perhaps requiring the manipulation of spacetime itself. Albert Einstein and Nathan Rosen, as we've discussed, originally proposed the idea of the Einstein-Rosen bridge, which laid the foundation for wormhole theory. However, neither Einstein nor Rosen believed that these bridges could be used for time travel. Their work was more focused on the structure of space-time itself. Physicist John Wheeler coined the term wormhole and expanded on the ideas of Einstein and Rosen. While Wheeler's research showed that wormholes were mathematically possible, he also suggested they might exist only on the quantum scale, far too small to be useful for time travel or human transportation. Roger Penrose has contributed to our understanding of space-time and black holes, but is highly skeptical of the practical use of wormholes for time travel. He believes that the extreme conditions required to create a stable wormhole are unlikely to exist naturally, and even less likely to be created artificially. Physicist Richard Feynman was less concerned with wormholes specifically, but introduced the idea of quantum mechanics, allowing for alternative paths in spacetime. His work on quantum electrodynamics hints at the possibility of strange behaviors in spacetime, though it doesn't directly support wormhole-based time travel. Neil deGrasse Tyson often discusses the possibility of time travel in his public lectures, noting that while the idea of wormholes is intriguing, it remains in the realm of speculation. He emphasizes that, without solid experimental evidence, wormholes and time travel are more science fiction than science fact for now. Brian Greene, a theoretical physicist known for his work on string theory, suggests that wormholes could potentially exist within the framework of higher dimensions. However, like many others, he points out that the exotic matter required to stabilize them presents a massive hurdle. Leonard Susskind, another prominent theoretical physicist, has worked extensively on black holes and quantum mechanics. While he's fascinated by the theoretical possibilities of wormholes, he's cautious about their practical use for time travel, noting that our understanding of space-time is still incomplete. Sean Carroll, a cosmologist and physicist, has voiced similar skepticism. He points out that even if wormholes exist, making them useful for time travel would require manipulating the fundamental structure of space-time in ways we don't yet understand. Lisa Randall, a theoretical physicist, has explored the idea of extra dimensions and how they might relate to wormholes. While she doesn't rule out the possibility of wormholes, she emphasizes that any real application of wormholes for time travel would likely require an understanding of dimensions beyond our current knowledge. Overall, while many physicists agree that wormholes are mathematically possible, there's significant debate about whether they could ever be used for time travel. The consensus is that while the idea is fascinating, the practical and theoretical obstacles are immense. Time travel via wormholes presents a number of daunting scientific challenges. The first major hurdle is the stability of the wormhole itself. Most wormhole solutions in general relativity suggest that they would collapse almost immediately after forming, making travel through them impossible without some means of keeping them open. To keep a wormhole stable long enough for time travel, exotic matter with negative energy would be required. However, we have no evidence that such exotic matter exists in the necessary quantities, and creating or harnessing it poses a challenge that is far beyond our current technology. Even if a stable wormhole could be created, controlling where and when it opens is another significant challenge. The laws of physics do not give us a clear mechanism for directing a wormhole to connect specific points in time or space. Without control, any journey through a wormhole could be random. Another issue is the enormous amount of energy that would likely be required to create and maintain a wormhole. Estimates suggest that the energy needed could exceed anything humanity could generate, even with our most advanced energy sources. Harnessing such power could require tapping into black holes or other extreme cosmic phenomena. There's also the problem of radiation. The intense gravitational fields around a wormhole could produce enormous amounts of radiation, potentially destroying any matter attempting to pass through. This makes the actual journey through a wormhole, even if it were stable, highly dangerous. The effects of time dilation further complicate the picture. As an object approaches the mouth of a wormhole, time may slow down relative to an outside observer. This could create complex time loops that make it difficult to predict when and where the traveler would emerge. Theoretical models suggest that wormholes might only allow travel into the future, not the past. While forward time travel is allowed under general relativity through effects like time dilation, backward time travel is far more problematic, as it could create paradoxes or violate causality. Quantum mechanics also raises challenges. While general relativity suggests that wormholes are possible, we don't yet have a theory of quantum gravity that fully reconciles the quantum world with the large-scale curvature of space-time. Without this, it's unclear how quantum effects would influence a wormhole. Some physicists believe that quantum effects would prevent wormholes from allowing time travel altogether. It's possible that the energy fluctuations at the quantum level could destabilize any wormhole, causing it to collapse before it could be used for time travel. Hawking's chronology protection conjecture also cast doubt on time travel via wormholes. He suggested that the laws of physics might include mechanisms to prevent time travel, perhaps through the buildup of energy or radiation that would block any attempt to travel to the past. Another challenge is the unknown nature of singularities. Wormholes are often associated with black holes, which contain singularities, points where the laws of physics break down. It's unclear what effect, if any, these singularities would have on a wormhole's stability or on a time traveler passing through. The concept of closed timelike curves, which are essential for backward time travel, also remains controversial. Even though they are mathematically possible in some solutions to general relativity, many physicists doubt whether they can exist in the real universe without violating the fundamental principles of causality. The second law of thermodynamics, which states that entropy always increases, could also be violated by time travel through wormholes. Traveling back in time could allow someone to decrease the overall entropy of the universe, which contradicts one of the most basic principles of physics. Even the sheer size of a stable wormhole could pose practical issues. If a wormhole large enough for a human or a spacecraft were created, it might distort the surrounding space-time to such an extent that it would affect everything around it, creating unpredictable consequences for the traveler and the environment. Despite these challenges, the possibility of time travel via wormholes remains an intriguing area of theoretical research. While the obstacles are enormous, they also push the boundaries of our understanding of the universe and could lead to new discoveries about the fundamental nature of space and time. Wormholes and black holes are both solutions to Einstein's equations of general relativity, but they represent very different phenomena in space-time. A black hole is a region where gravity is so strong that nothing, not even light, can escape, while a wormhole is a hypothetical tunnel through space-time, potentially connecting distant parts of the universe. The most striking difference is that black holes are well documented and observed in the universe, while wormholes remain purely theoretical. Black holes have been detected through their effects on nearby matter and light, but no direct evidence for wormholes has yet been found. Black holes form from the collapse of massive stars at the end of their life cycle, creating a singularity, a point where gravity becomes infinite. Wormholes, on the other hand, are predicted to be shortcuts through space-time with no singularity in the center. The event horizon of a black hole marks the boundary beyond which nothing can return. If you cross the event horizon, you're inevitably pulled toward the singularity. Wormholes, however, wouldn't necessarily have an event horizon, allowing travel back and forth between their two ends, if they can be stabilized. Black holes are considered dangerous and destructive, with their immense gravitational forces capable of tearing apart anything that comes too close. In contrast, a traversable wormhole, if it existed, could theoretically allow safe passage through space-time without causing harm to the traveler. A black hole only pulls things inward, trapping everything that crosses its event horizon. A wormhole, by contrast, is thought to connect two separate regions of space-time, allowing matter to pass through and emerge on the other side, potentially far away from its original location. The formation of black holes is a well-understood process tied to stellar evolution and the collapse of massive stars. Wormholes, however, would require exotic matter with negative energy to remain open, something that has not been observed in nature. Wormholes, if they exist, could be used as shortcuts through space, connecting distant parts of the universe almost instantly. Black holes, on the other hand, are not passageways but dead ends where everything is crushed into the singularity. While black holes can grow in size as they pull in more matter, a wormhole would need to be carefully balanced with exotic matter to prevent it from collapsing. This difference in structure highlights the difficulty in making wormholes a practical means of travel. The gravitational fields around black holes are well studied and observed, especially through gravitational waves and the bending of light. The gravitational behavior of a wormhole would likely be very different, possibly creating unique distortions in spacetime that we haven't yet detected. In black holes, time behaves strangely, slowing down near the event horizon. Time travel through a wormhole, however, could allow for shortcuts not just through space, but through time as well, depending on how the wormhole connects different regions of space-time. Another major difference is that black holes can be found across the universe, with supermassive black holes residing at the centers of galaxies. Wormholes, if they exist, might be much rarer and more difficult to detect, hidden in the fabric of space-time itself. Black holes can be observed indirectly by studying the motion of stars and gas clouds around them, or through the detection of gravitational waves. Wormholes would be much more elusive, potentially only revealing themselves through subtle effects on light, gravity, or radiation. In science fiction, wormholes are often depicted as gateways for interstellar travel, offering a way to bypass the limitations of light speed. Black holes, on the other hand, are portrayed as dangerous traps, and while real, they offer no hope for travel or exploration. While black holes are a natural outcome of the known laws of physics, wormholes challenge our understanding of space-time, requiring new physics, exotic matter, or advanced technology to even consider them as real traversable objects. Event horizons and singularities are two fundamental aspects of black holes that distinguish them from other objects in space. The event horizon is the boundary surrounding a black hole, marking the point where nothing can escape its gravitational pull. Once something crosses this threshold, it's gone forever, trapped by the black hole's intense gravity. Singularities, on the other hand, are the heart of a black hole. At the singularity, gravity becomes infinitely strong, and space-time itself is thought to collapse into a single point. The laws of physics as we know them break down at the singularity, making it one of the most mysterious concepts in astrophysics. The event horizon is often described as a one-way door. Once you pass through it, you can't get back out, because the escape velocity inside the event horizon exceeds the speed of light. Not even light can escape, which is why black holes appear completely black to outside observers. In contrast, wormholes, if they exist, wouldn't necessarily have an event horizon. This would mean that you could, in theory, enter and exit a wormhole without being trapped inside. The absence of an event horizon is what makes wormholes theoretically traversable, while black holes are not. The singularity at the center of a black hole is where all the matter and energy are crushed into an infinitely dense point. This is where the curvature of space-time becomes infinite, and any object approaching the singularity would be stretched and torn apart by the extreme gravitational forces. In a wormhole, there is no singularity like that found in a black hole. Instead of collapsing into a point of infinite density, the wormhole's structure is thought to remain intact, assuming the presence of exotic matter that prevents it from collapsing. The event horizon creates a clear boundary between the inside and outside of a black hole. For an outside observer, time appears to slow down as an object approaches the event horizon, creating a strange distortion of time near the black hole. At the singularity, all known laws of physics break down. Quantum mechanics and general relativity, which describe the universe at different scales, fail to provide a complete picture of what happens at this infinitely dense point. This is one of the reasons black holes remain such a rich field of study. Wormholes, on the other hand, don't have the same kind of singularity at their core. Instead of pulling everything into a point of no return, a wormhole would theoretically allow passage to another region of space-time, avoiding the destructive effects of a singularity. The gravitational pull near the event horizon of a black hole is so strong that nothing can move fast enough to escape it. This creates the no-escape zone, a defining feature of black holes, while wormholes are thought to offer an escape route to a different part of the universe. The singularity is hidden behind the event horizon, meaning that no information can escape from it. This is what creates the famous information paradox, a puzzle in theoretical physics about whether information that falls into a black hole is lost forever or somehow preserved. In wormhole models, there is no equivalent of an event horizon or singularity that would trap information. This makes them intriguing as potential shortcuts through space-time, although we have yet to find evidence that such stable structures can exist. The event horizon itself is invisible, but we can detect its effects on nearby objects. Stars, gas clouds, and even light behave strangely near the event horizon, curving around it in ways that let us infer the black hole's presence and size. In contrast, wormholes, if they exist, would likely create subtle distortions in space-time, but wouldn't have the same dramatic effects as a black hole's event horizon. Their effects would be more like bending or warping space rather than pulling everything in. The study of event horizons and singularities continues to deepen our understanding of space-time, gravity, and the limits of physics. Whether we're studying black holes or exploring the possibility of wormholes, these extreme environments push the boundaries of what we know about the universe. Einstein-Rosen bridges, often referred to as wormholes, are theoretical structures that emerged from solutions to Einstein's equations of general relativity. These bridges were originally proposed as connections between black holes and other regions of space-time. The connection between black holes and Einstein-Rosen bridges lies in the extreme curvature of space-time near these objects. A black hole forms from the collapse of a massive star, creating a singularity at its center where gravity becomes infinitely strong. The Einstein-Rosen bridge represents a tunnel-like connection that could theoretically link this singularity to another point in space-time, creating a kind of cosmic shortcut. This connection is purely theoretical, as the Einstein-Rosen bridge is not traversable in its original form. When Einstein and Rosen first described this bridge, they envisioned it as a type of wormhole, but they realized it would collapse too quickly for anything to pass through it. In the context of black holes, the bridge would exist only for an instant, pinching off before matter or information could cross from one side to the other. This makes the Einstein-Rosen bridge different from the traversable wormholes often imagined in science fiction. The idea of linking black holes to other regions of space-time through an Einstein-Rosen bridge raises intriguing possibilities about the nature of singularities. Some physicists have speculated that these bridges could connect black holes to white holes, objects that theoretically expel matter rather than pull it in. A white hole, if it exists, would be the opposite of a black hole, and an Einstein-Rosen bridge could be the connection between the two. However, no evidence for white holes has ever been observed, and the instability of the Einstein-Rosen bridge makes this connection speculative at best. One of the reasons this bridge collapses so quickly is due to the extreme gravitational forces near the event horizon of a black hole. Without exotic matter to keep the bridge stable, it would close almost as soon as it formed, trapping anything inside. Despite this, the concept of an Einstein-Rosen bridge laid the groundwork for later studies of wormholes and other exotic space-time structures. It helped physicists realize that space-time could, in theory, be connected in ways that seem impossible under normal conditions. The bridge also highlighted the similarities and differences between black holes and wormholes. Both involve the bending of space-time, but black holes trap everything that crosses the event horizon, while a stable wormhole would offer a passage through space. In later years, physicists like Kip Thorne expanded on the idea of traversable wormholes, showing how exotic matter could be used to hold the wormhole open. This builds on the foundation set by the Einstein-Rosen bridge, but aims to overcome its inherent instability. The connection between black holes and Einstein-Rosen bridges also deepens our understanding of gravity. Black holes represent a point where gravity becomes so strong that even the structure of space-time itself warps in extreme ways, creating the conditions for such a bridge. If Einstein-Rosen bridges could somehow be stabilized, they would offer a way to connect distant points in space, possibly providing a method for faster-than-light travel or even time travel. However, this remains purely theoretical, as the technology or conditions needed to stabilize such a bridge are far beyond our current reach. Einstein-Rosen bridges also challenge our understanding of singularities. While black holes have singularities at their core, a wormhole would need to avoid this destructive point to allow passage through it, creating a conflict between the known properties of black holes and the theoretical nature of wormholes. This theoretical connection between black holes and Einstein-Rosen bridges continues to inspire research in both general relativity and quantum mechanics. It pushes scientists to explore the limits of spacetime and to imagine new possibilities for how the universe is structured. Though the Einstein-Rosen bridge itself may not offer a viable path for travel, it remains a crucial concept in the ongoing study of how gravity and spacetime interact at the most extreme scales. It links the known physics of black holes with the speculative realm of wormholes, bridging the gap between observation and theory. Some physicists have speculated that black holes could be entrances to wormholes, offering a gateway to another region of space or even a different universe. This idea stems from the fact that black holes warp space-time so intensely, which could theoretically allow for the creation of a tunnel-like structure. If a black hole were connected to a wormhole, its event horizon might serve as the entrance to the wormhole's throat, but crossing it would be extremely dangerous. The intense gravitational forces inside the event horizon would likely destroy anything attempting to enter. The idea of black holes as wormhole entrances gained attention due to the similarities in how both phenomena bend space-time. However, without exotic matter to keep the wormhole stable, a black hole wormhole would collapse too quickly to be useful for travel. Some theories suggest that certain types of black holes, particularly rotating black holes or Kerr black holes, might be more likely to form wormholes. The spinning motion of a Kerr black hole could create the conditions necessary for a stable wormhole throat, although this is still highly speculative. Even if black holes were entrances to wormholes, the challenge would be surviving the journey. The singularity at the center of a black hole creates a point of infinite density, and the extreme tidal forces would likely tear apart anything that ventured too close. There's also the possibility that a black hole might be connected to a white hole, with the wormhole acting as the tunnel between the two. A white hole is the theoretical opposite of a black hole, expelling matter rather than pulling it in, but no evidence for white holes has ever been found. If such a connection existed, entering a black hole could mean exiting through a white hole in another part of the universe. This raises the intriguing possibility that black holes could be portals, though the extreme conditions inside make it unlikely that anything would survive the passage. Some physicists have explored whether the inside of a black hole could contain the exotic matter needed to stabilize a wormhole. This would allow the black hole to act as a wormhole entrance, but we currently have no way of testing this hypothesis. Observationally, black holes appear to trap everything that comes near them, with no sign of matter or energy emerging elsewhere. This suggests that if black holes are connected to wormholes, the connection is either extremely rare or hidden beyond what we can observe. Another challenge is that black holes have event horizons, which prevent any information from escaping. If a black hole were an entrance to a wormhole, this event horizon would still pose a barrier, as nothing can cross back once it's entered. Even though the idea of black holes as wormhole entrances is compelling, the physics of black holes doesn't easily allow for such a connection. The presence of a singularity at the center, along with the collapse of any potential Einstein-Rosen bridge, makes stable passage through a black hole unlikely. In science fiction, black holes are often portrayed as gateways to other dimensions or distant parts of the universe, but this remains far from proven in the realm of real-world physics. The theoretical models that link black holes to wormholes are still incomplete. For black holes to function as wormhole entrances, there would need to be a way to prevent the collapse of the wormhole's throat. This requires exotic matter with negative energy, but no such matter has ever been detected near black holes. Current research continues to explore the possibility, especially in the context of quantum gravity. If a theory of quantum gravity can reconcile the extreme conditions inside black holes with the structure of wormholes, it could open up new insights into both phenomena. For now, the connection between black holes and wormholes remains a fascinating but unproven idea. It pushes the boundaries of our understanding of spacetime, offering a glimpse into the deeper mysteries of the universe. If black holes could indeed be entrances to wormholes, the implications for our understanding of space and time would be profound. It would mean that black holes are not just dead ends in space, but potentially gateways to other parts of the universe, or even other universes. One of the most significant implications would be the possibility of faster-than-light travel. If a black hole wormhole could connect two distant regions of space, it might allow travel between them in a fraction of the time it would take to travel through normal space. This would challenge the very foundations of Einstein's theory of relativity, which states that nothing can travel faster than light in a vacuum. A wormhole connection would bypass this limitation, not by breaking the speed of light, but by taking a shortcut through space-time. The existence of black hole wormholes could also offer new insights into the nature of singularities. Rather than being points where space-time breaks down entirely, singularities might be part of a larger structure that connects different regions of the universe through wormholes. If black hole wormholes exist, they might allow us to study regions of space that are otherwise unreachable. For example, they could provide a way to observe distant galaxies, other universes, or even regions of space-time where the laws of physics are different from our own. Another important implication is the possibility of time travel. If a wormhole connects not just 2 points in space, but 2 different points in time, it could theoretically allow for movement between the past and the future, raising questions about causality and paradoxes. Theoretical models suggest that if a black hole wormhole could be stabilized, it might allow for travel to parallel universes. This idea opens up the possibility that black holes could be connections between not just distant regions of our universe, but entirely different realities. Black hole wormholes could also provide answers to some of the biggest mysteries in cosmology, such as the nature of dark matter and dark energy. If black holes are connected to other parts of space or other universes, it might explain where some of the universe's missing mass and energy has gone. On the quantum scale, the implications of black hole wormholes could help bridge the gap between general relativity and quantum mechanics. Understanding how space-time behaves inside a black hole wormhole could provide clues to developing a theory of quantum gravity. The potential to use black hole wormholes for interstellar travel would revolutionize space exploration. Instead of requiring centuries or millennia to reach distant stars, wormholes could make such journeys possible within human lifetimes, transforming our ability to explore the cosmos. However, the extreme conditions near a black hole wormhole would likely make travel through it incredibly dangerous. The gravitational forces alone could tear apart any spacecraft, unless we find a way to manipulate or shield against these forces. Theoretical black hole wormholes also raise questions about the fate of matter and information that falls into a black hole. If black holes are connected to other parts of the universe through wormholes, then matter might not be lost forever, but instead transferred to another location. The idea of black hole wormholes also touches on the information paradox, a problem in physics that questions whether information that enters a black hole is destroyed or preserved. If wormholes exist, they could offer a resolution by suggesting that information is not lost, but rather transferred through the wormhole. If black hole wormholes exist, they might also have played a role in the early universe, possibly influencing the formation of galaxies and large-scale cosmic structures. Theoretical physicists continue to explore whether these wormholes could have been important during the universe's inflationary period. Ultimately, the theoretical implications of black hole wormholes challenge our understanding of the universe in nearly every way. They force us to rethink the nature of space, time, and gravity, and offer tantalizing possibilities for future discoveries in cosmology and quantum physics. A traversable wormhole is one that allows matter or information to pass through safely from one side to the other without collapsing. The key to making a wormhole traversable lies in its stability, and this is where exotic matter with negative energy comes into play. Without it, the wormhole would pinch off almost immediately after forming. Exotic matter is theorized to provide the negative energy needed to counteract the wormhole's natural tendency to collapse under its own gravitational forces. This would keep the throat of the wormhole open long enough for someone or something to travel through it. For a wormhole to be traversable, it also needs to avoid creating destructive forces inside its throat. In many theoretical models, the gravitational pull inside a wormhole is so extreme that it would stretch and tear apart any object passing through, much like spaghettification near a black hole's singularity. A traversable wormhole must have a structure that minimizes these tidal forces, allowing a smooth passage through space-time. This could be achieved if the exotic matter within the wormhole creates a repulsive force, pushing back against the intense gravitational pull. The size of the wormhole's throat is another critical factor. For humans or spacecraft to pass through, the throat needs to be large enough to allow matter to travel without being compressed or crushed. If the throat is too narrow, nothing larger than subatomic particles would be able to pass through. Time dilation, another effect of strong gravitational fields, must also be controlled in a traversable wormhole. If time moves too slowly near the wormhole's mouth, a traveler might experience significant time differences relative to the outside universe, creating complications for practical use. Another aspect to consider is whether the wormhole allows for two-way travel. Some models suggest that a traversable wormhole might only permit movement in one direction, limiting its usefulness for interstellar travel or communication. To be truly practical, the wormhole must be stable in both directions. For traversability, the wormhole's entrances, or mouths, need to remain fixed in space-time. If the mouths are constantly moving or shifting, the wormhole could become unusable. Ensuring stability on both ends is a significant challenge for any theoretical wormhole. The wormhole would also need to avoid creating dangerous levels of radiation inside its throat. High-energy particles and radiation could be trapped in the wormhole, potentially creating deadly conditions for anything trying to pass through. The journey through a traversable wormhole must also be relatively short compared to the time it would take to travel the same distance through regular space. If traveling through the wormhole takes just as long or longer, it loses its advantage as a shortcut. One of the most significant theoretical challenges is keeping the wormhole stable over time. Even if exotic matter can hold the throat open initially, there's no guarantee that it will remain stable indefinitely. The wormhole could gradually shrink or close, stranding travelers inside. To make a wormhole traversable, it would also need to avoid creating paradoxes, especially if time travel is involved. Some wormhole models suggest that they could connect different points in time as well as space, raising concerns about causality and time loops. The energy requirements for creating and maintaining a traversable wormhole are another critical hurdle. Estimates suggest that the amount of exotic matter needed could be astronomical, far beyond anything we could generate or control with current technology. Additionally, a traversable wormhole must be accessible. If the entrances are hidden deep inside a black hole or in a distant, unreachable region of space, it would be of little practical use for space exploration or travel. In the end, making a wormhole traversable involves overcoming several major scientific and technological challenges, from stability and size to energy requirements and safety concerns. While it remains a fascinating possibility, creating a functional, traversable wormhole is far from achievable with our current understanding of physics. The Thorne-Morris wormhole solution was developed by physicists Kip Thorne and Michael Morris in the 1980s. Their work aimed to explore whether a stable, traversable wormhole could exist within the framework of general relativity. They specifically focused on finding solutions that would allow for safe passage through the wormhole. In their model, a key requirement for maintaining a traversable wormhole is the presence of exotic matter. This exotic matter would have negative energy, which is necessary to counteract the gravitational forces that would otherwise cause the wormhole to collapse. Thorne and Morris proposed that if enough exotic matter could be found or created, it would keep the throat of the wormhole open, allowing travelers to move through it without being crushed by the intense gravitational forces inside. This was one of the first models to offer a solution to the problem of wormhole stability. Their solution also emphasized that the wormhole needed to have no event horizon. This would ensure that anything entering the wormhole wouldn't be trapped forever, as it would be with a black hole. In their model, both ends of the wormhole would remain open and accessible. A crucial aspect of the Thorne-Morris solution is that the wormhole's throat would need to be wide enough for practical travel. The size of the throat determines whether humans or spacecraft could pass through, and Thorne and Morris calculated that the throat could be kept large with sufficient exotic matter. The Thorne-Morris solution also considered the issue of tidal forces. In many theoretical wormholes, the tidal forces near the throat would be so strong that they would tear apart anything trying to pass through. Thorne and Morris calculated that these forces could be minimized, making travel through the wormhole theoretically safe. One of the most significant outcomes of their work was the realization that wormholes, if stable, could connect not just distant points in space, but also different points in time. This raised the possibility that the Thorne-Morris wormhole could be used for time travel. However, the energy required to create and stabilize such a wormhole would be enormous. Thorne and Morris acknowledged that while their solution was mathematically sound, The practical challenges of finding or generating enough exotic matter made the idea far from feasible with current technology. Their work also highlighted the issue of causality. If a wormhole allows time travel, it could create paradoxes, such as the possibility of altering the past. The Thorne-Morris solution didn't fully resolve these concerns, but it opened the door to further exploration of time travel within general relativity. Despite these challenges, the Thorne-Morris solution remains one of the most important theoretical models for a traversable wormhole. It provided a framework for how such a structure could exist, even though it remains speculative and unproven in practice. The solution also sparked a wider interest in wormholes, influencing both scientific research and popular culture. Thorne's involvement in films like Interstellar helped bring the concept of traversable wormholes into the public imagination, further popularizing the idea. Another aspect of the Thorne-Morris wormhole is that it would need to be carefully stabilized. Even small disturbances could cause the exotic matter to lose its effectiveness, leading to the collapse of the wormhole. This makes the solution fragile, requiring precise conditions for stability. Their model also predicted that the wormhole could potentially be held open indefinitely, as long as the exotic matter remained in place. This means that if we could find a way to harness negative energy, wormholes could be permanent features of space-time. The Thorne-Morris wormhole solution doesn't just explore the possibilities of space travel, it also challenges our understanding of the universe. It raises questions about the fundamental nature of space-time, gravity, and the limits of what's possible within the laws of physics. While the Thorne-Morris wormhole solution hasn't led to the discovery of actual wormholes, it remains a cornerstone of theoretical physics. It provides a glimpse into how wormholes could exist, even if we're far from turning this theory into reality. For a wormhole to remain stable and traversable, it requires the presence of exotic matter. Exotic matter is unlike any ordinary matter we encounter. It has negative energy density, which is necessary to keep the wormhole's throat open against the immense gravitational forces that would otherwise cause it to collapse. This negative energy would exert a repulsive gravitational force, counteracting the natural tendency of space-time to pinch off the wormhole. Without it, the walls of the wormhole would rapidly close in, making passage through it impossible. The need for exotic matter arises from the fact that traditional matter, with its positive energy density, would only increase the gravitational pull, leading to a collapse. Only matter with negative energy can produce the repulsive force needed to keep the wormhole open and stable. One of the theoretical ways exotic matter could be generated is through quantum effects, such as the Casimir effect. In this effect, negative energy is created in the vacuum between two closely spaced objects, but the amount produced is minuscule, far too small to stabilize a wormhole. The amount of exotic matter required to stabilize a macroscopic wormhole large enough for human travel would be enormous. Current estimates suggest that the energy needed could exceed the total output of all the stars in a galaxy, making it far beyond our current technological capabilities. Moreover, exotic matter would need to be distributed precisely around the wormhole's throat to maintain stability. Any imbalance in the distribution could cause the wormhole to collapse or become unstable, potentially trapping anything inside it. Another challenge with exotic matter is that it's purely theoretical at this point. Although quantum mechanics predicts its possible existence, we have not observed or produced exotic matter in any meaningful quantity that could be used for practical purposes like wormhole stabilization. In addition to its role in preventing collapse, exotic matter could also help reduce tidal forces within the wormhole. These forces could otherwise stretch and tear apart anything passing through the throat, making travel impossible. Exotic matter's repulsive properties might mitigate these forces, allowing for safe passage. If exotic matter does exist, it might not be easily accessible or found naturally in the universe. This raises the question of whether we could ever create it artificially, and if so, how we would harness and contain it to stabilize a wormhole. Theoretical physicists have also explored whether exotic matter could be linked to dark energy or dark matter, both of which are mysterious components of the universe. If dark energy exhibits negative energy properties, it might serve as a potential source of the exotic matter needed for a stable wormhole. However, even if exotic matter could be found or created, maintaining a stable wormhole would require constant input of negative energy. Any fluctuation in the exotic matter's properties could destabilize the wormhole, causing it to collapse and potentially destroy anything inside it. The exotic matter also raises questions about energy conservation. In classical physics, the creation of negative energy seems to violate the principle of conservation of energy, which complicates how exotic matter could be sustained in a real-world scenario. In quantum theories, exotic matter might be more plausible, as quantum fluctuations could allow for temporary violations of energy conservation. But scaling these effects up to a usable level remains one of the biggest challenges facing the concept of a traversable wormhole. The presence of exotic matter would also affect the geometry of spacetime near the wormhole, possibly creating strange effects like time dilation or unusual gravitational forces around the wormhole's entrance. This could further complicate efforts to control or stabilize a wormhole. Ultimately, exotic matter is the key to making traversable wormholes possible, but its existence and practical application remain one of the greatest unknowns in theoretical physics. Without it, wormholes remain a tantalizing but unreachable concept, far beyond our current technological grasp. If wormholes could be made traversable, the methods for traveling through them would require overcoming a series of immense challenges. First, entering the wormhole would mean approaching its mouth, which would likely be surrounded by intense gravitational fields. Any spacecraft or traveler would need to withstand these forces without being torn apart. The spacecraft would also have to be equipped with a technology capable of navigating the spacetime distortions around the wormhole. Normal propulsion methods might not work, as space itself would be warped in unpredictable ways. This might require entirely new kinds of engines or manipulation of gravity. Once inside the wormhole, the craft would need to pass through the throat without being affected by any tidal forces. In some models, exotic matter within the wormhole could help neutralize these forces, but it would be essential to avoid sections of the throat where the gravitational pull could still be extreme. Time dilation might also become an issue. Depending on the strength of the gravitational fields near the wormhole's entrances, time could pass differently inside the wormhole compared to the outside universe. Travelers might emerge to find that decades or centuries have passed while they were in transit. Navigating the exit of a wormhole could present its own set of challenges. The location of the other mouth might be in a completely different part of the universe, far from any familiar stars or landmarks. Advanced navigation systems would be necessary to determine where the wormhole has led. To travel safely through a wormhole, it's likely that the craft would need to be specially designed to withstand both the entrance and the interior conditions. This could mean using advanced shielding technologies or even materials that interact with exotic matter in a way that stabilizes the wormhole during transit. Another hypothetical method for traversing a wormhole involves the manipulation of the wormhole itself. If we could control the exotic matter that stabilizes the wormhole, it might be possible to open and close it at will, directing where and when the wormhole connects different regions of space. Artificially creating a wormhole might also be considered, though this would require energy levels far beyond anything humanity can currently produce. Some theoretical models suggest that creating a stable wormhole could involve harnessing the power of black holes, or even manipulating quantum fields at an extremely small scale. Once a wormhole is stable, communication through it could be a first step before attempting full physical travel. Sending signals or robotic probes through a wormhole might help determine whether it's safe for human travel, providing valuable data on the stability and conditions within the tunnel. Some models of wormhole travel suggest that, once entered, the traveler would experience little or no sensation of movement. Because the wormhole connects two distant points in space directly, there would be no acceleration or deceleration during the journey, unlike traditional space travel. If wormholes could connect not just different points in space, but different points in time, the method of travel would also need to account for the potential of arriving in a different era. Time travel through wormholes raises questions about causality, and travelers might have to navigate the implications of arriving in the past or future. In practical terms, the first attempts at wormhole travel might involve sending small, durable objects or machines through rather than humans. These probes could collect data on the conditions inside the wormhole and help refine methods for safe travel. Another consideration is the return journey. In many theoretical wormholes, travel might be one way, with the wormhole collapsing after a single use, or with no guarantee that it would lead back to the original location. Developing a way to ensure a stable round trip would be essential for practical exploration. Hypothetical wormhole travel also involves considering the potential hazards at the other end. The exit of a wormhole could open into extreme environments, such as the interior of a star or a black hole, meaning that precise control over the wormhole's destination would be critical. Ultimately, the methods for traveling through wormholes are still in the realm of theory. They depend on our ability to solve the immense technological and physical challenges of stabilizing a wormhole, navigating its interior, and ensuring a safe passage through the vast distortions of space-time. The main problem with traversability is the instability of the wormhole itself. Without exotic matter to keep the throat open, the wormhole would collapse in on itself almost instantly. This collapse would create forces so extreme that anything inside would be destroyed before completing the journey. Even if the wormhole remains stable, the intense gravitational forces at the mouth could be lethal. These forces would create powerful tidal effects, stretching and compressing any matter that gets too close. This spaghettification effect would make it nearly impossible for a human to survive the entry. Radiation is another significant threat. The high-energy environment around a wormhole's mouth could be filled with dangerous levels of cosmic rays or other forms of radiation. Passing through these zones without adequate protection could cause severe damage to both humans and spacecraft. Inside the wormhole, conditions might be equally hostile. The space-time curvature could produce unpredictable gravitational forces, making the passage turbulent and dangerous. Any sudden shifts in these forces could destroy the spacecraft or harm its passengers. Another major challenge is the lack of control over where or when the wormhole leads. If the destination is unpredictable, travelers might emerge in the middle of a hostile environment, such as a black hole or the interior of a star. Survival would depend on the ability to navigate such hazards. Time dilation could also create problems for human survival. Depending on the gravitational conditions at either end of the wormhole, time may pass differently for the traveler compared to the outside universe. A short trip through the wormhole might mean returning to find that years or even centuries have passed. Additionally, there's the issue of communication. Once inside the wormhole, it may be impossible to send signals back through to the other side. This communication blackout could make it difficult for mission control to monitor the traveler's progress or offer assistance in case of emergency. Psychological challenges would also come into play. The disorienting experience of traveling through distorted space-time, combined with isolation and the unknown dangers at the other end, could have severe mental health impacts on travelers. Preparing for these effects would be just as important as protecting against physical hazards. Energy requirements add another layer of complexity. Keeping a wormhole open long enough for safe travel would likely require vast amounts of energy, far beyond anything we can currently generate. Without a reliable energy source, a stable and safe passage may be impossible. The risk of the wormhole closing unexpectedly also poses a serious threat. If the exotic matter maintaining the throat were to fluctuate or fail, the wormhole could collapse while travelers are still inside, potentially trapping them in an unknown region of space-time or crushing them in the process. Even the act of passing through a wormhole might involve unforeseen biological risks. Exposure to extreme gravitational or quantum effects could have unknown impacts on the human body, altering cells or DNA in unpredictable ways. Long-term survival may depend on advanced medical precautions. The spacecraft itself would need to be designed to withstand both the intense gravitational distortions and the unknown conditions on the other side. Conventional materials and construction methods might not be sufficient to protect against the forces encountered during a wormhole journey. Navigation within the wormhole presents its own set of problems. With space-time warping in unpredictable ways, it might be impossible to steer a spacecraft or control its path once inside. This lack of control increases the likelihood of emerging in an unintended or dangerous location. Temperature fluctuations could also pose a significant threat. The conditions near the mouth of a wormhole or inside its throat might involve extreme heat or cold, requiring advanced thermal protection to ensure the safety of both the craft and its occupants. In the end, human survival through a traversable wormhole hinges on solving these myriad problems. From stabilizing the wormhole itself to protecting travelers from radiation, gravity, and time dilation. The challenges are vast, making the dream of safe wormhole travel seem distant for now. Quantum mechanics plays a crucial role in the theoretical understanding of wormholes, particularly when it comes to stabilizing them. In classical general relativity, a wormhole would collapse almost instantly after forming. Quantum mechanics, however, introduces the possibility of preventing this collapse through quantum effects. One of the most important ideas comes from the concept of quantum fluctuations. In empty space, particles and energy constantly pop in and out of existence. These fluctuations could, in theory, generate the negative energy needed to stabilize a wormhole's throat, keeping it open for longer periods. The relationship between quantum mechanics and wormholes becomes especially important when considering the exotic matter required for stability. Quantum theory suggests that exotic matter could arise from these fluctuations, providing the necessary repulsive forces to keep the wormhole open. Quantum tunneling is another concept that could be relevant. In quantum mechanics, particles can pass through barriers they would not normally be able to cross. This phenomenon could, in theory, apply to wormholes, allowing particles or even information to move through them under certain conditions. The famous connection between wormholes and quantum entanglement adds another layer of complexity. Some physicists have proposed that wormholes and entangled particles might be two sides of the same coin. This is often referred to as the ER-EPR conjecture, which suggests that quantum entanglement and wormholes are related at a fundamental level. In this view, wormholes could serve as a kind of bridge between entangled particles, allowing instantaneous communication across vast distances. This idea is speculative, but it opens up new possibilities for how quantum mechanics might allow for the existence of traversable wormholes. Another critical aspect of quantum mechanics in wormhole theory is the potential for quantum gravity. While general relativity describes gravity on large scales, quantum mechanics governs the subatomic world. A theory of quantum gravity might reconcile these two, providing insights into how wormholes could form and remain stable at quantum scales. Hawking radiation, a quantum mechanical process that occurs near black holes, also connects to wormhole theory. If quantum processes can cause black holes to emit radiation, they might similarly influence wormholes, potentially stabilizing them or providing a method for detecting them. Some physicists suggest that wormholes could exist on the quantum scale, far too small to be detected by current instruments. These quantum wormholes might flicker in and out of existence, acting as temporary connections between different parts of spacetime. Quantum field theory also plays a role in understanding how matter and energy behave near the throat of a wormhole. The intense gravitational fields near a wormhole could distort quantum fields, potentially allowing for the creation of exotic matter needed to keep the wormhole traversable. Quantum mechanics might also help solve some of the paradoxes associated with wormhole travel. In classical physics, time travel through wormholes creates issues with causality, but in the quantum world, where probabilities and uncertainties dominate, these paradoxes might be avoided or resolved. Quantum fluctuations could also create temporary microscopic wormholes known as Einstein-Rosen bridges. While these wormholes would be too small for humans to travel through, their existence suggests that wormholes are at least theoretically possible in the quantum realm. The interplay between quantum mechanics and general relativity remains one of the greatest challenges in modern physics. Understanding how these two theories interact could be the key to unlocking the mystery of wormholes and other exotic space-time phenomena. Finally, any future theory of quantum gravity will likely provide a deeper understanding of wormholes. Such a theory could explain how space-time behaves at the smallest scales, and might reveal whether wormholes are a natural part of the quantum structure of the universe. In summary, quantum mechanics is essential for exploring the possibility of wormholes. While many aspects remain theoretical, the principles of quantum physics offer hope that, one day, we may discover how to stabilize and travel through these fascinating structures. Quantum foam, also known as space-time foam, is a concept that arises from quantum mechanics and suggests that space-time is not smooth and continuous at the smallest scales. Instead, at the quantum level, space-time is thought to be constantly fluctuating, filled with tiny distortions and bubbles of energy. These fluctuations could potentially create what are known as micro-wormholes. These tiny wormholes would be incredibly small, likely smaller than subatomic particles, and would appear and disappear in a fraction of a second, popping in and out of existence as part of the quantum foam. Micro-wormholes, if they exist, might act as tiny connections between different points in spacetime. However, because they are so small and fleeting, they would not be traversable in any practical sense, at least not for anything larger than a fundamental particle. The idea of quantum foam comes from the uncertainty principle in quantum mechanics, which states that energy and spacetime can fluctuate at extremely small scales. These fluctuations create a chaotic environment where space and time blur, potentially giving rise to micro-wormholes. In theory, these micro-wormholes could allow particles to tunnel through spacetime, traveling between different regions without crossing the intervening space. While this is purely speculative, it aligns with other quantum mechanical phenomena, like quantum tunneling. Quantum foam suggests that at the Planck scale, which is the smallest scale of the universe, spacetime behaves very differently from what we observe at macroscopic scales. This chaotic environment might be the birthplace of countless tiny wormholes that constantly form and collapse. Because micro-wormholes are so small, detecting them is currently impossible with our existing technology. Even if they do exist, they would be incredibly difficult to observe directly, as they would appear and vanish within an incredibly short amount of time. Some theories suggest that micro-wormholes could have an effect on the behavior of particles at quantum scales, possibly influencing phenomena like quantum entanglement. If this is the case, it could provide indirect evidence for the existence of these tiny wormholes. Another intriguing possibility is that these micro-wormholes could play a role in the fabric of the universe itself, connecting distant parts of space-time on the quantum level. If this is true, then space-time might be more interconnected than it appears at larger scales. While micro-wormholes would not be traversable in the same way as the larger theoretical wormholes we imagine in science fiction, they still offer insight into the structure of space-time. They could represent the building blocks of how space and time interact at the quantum level. Some physicists believe that if we can better understand quantum foam and micro-wormholes, we might unlock new insights into quantum gravity, the theory that aims to unify quantum mechanics with general relativity. This could be the key to understanding how gravity works on the smallest scales. Micro-wormholes might also be connected to the concept of virtual particles, which appear and disappear in quantum fields. If these virtual particles pass through micro-wormholes, it could provide a new perspective on how quantum processes are linked to the underlying fabric of spacetime. The existence of quantum foam and micro-wormholes would have profound implications for our understanding of the universe. It would suggest that spacetime is not a static backdrop, but an ever-changing dynamic field where quantum effects play a fundamental role. Some speculative theories even suggest that micro-wormholes might be harnessed in the distant future for advanced technologies, though this idea remains in the realm of science fiction for now. Such technologies might involve manipulating spacetime at the quantum level. Ultimately, micro-wormholes represent one of the most fascinating possibilities in the quantum description of spacetime. While we are far from proving their existence, they remain a compelling aspect of quantum mechanics, hinting at the hidden complexities of the universe's smaller scales. Quantum entanglement is a phenomenon where two particles become linked in such a way that the state of one instantly affects the state of the other, no matter how far apart they are. This connection seems to operate faster than the speed of light, leading some physicists to draw parallels between entanglement and wormholes. One intriguing idea is that entanglement could be the quantum equivalent of a wormhole. In this view, the particles are connected through a tiny wormhole in space-time, allowing them to communicate instantaneously, even across vast distances. This concept is known as the ER-EPR conjecture. The ER-EPR conjecture was proposed by physicists Juan Maldacena and Leonard Susskind. It suggests that Einstein-Rosen bridges, which are a type of wormhole, might be fundamentally connected to Einstein-Podolsky-Rosen pairs, which describe entangled particles. Essentially, wormholes and entanglement could be two aspects of the same underlying phenomenon. If this connection holds true, it would mean that quantum entanglement might involve some form of space-time bridge between particles. While these wormholes would be far too small to traverse, they might offer a new way of understanding how space-time operates at the quantum level. One implication of this theory is that space-time itself might be composed of an intricate network of quantum entanglements. These entangled connections could form the structure of space-time, linking distant points in ways that challenge our classical understanding of how the universe is organized. The idea of wormholes as connections between entangled particles also raises questions about faster-than-light communication. While quantum entanglement does not allow information to be transmitted faster than light in the traditional sense, if it's linked to wormholes, it could hint at new possibilities for instantaneous connections across space. This theory also suggests that if we could manipulate quantum entanglement on a large scale, we might be able to create or influence wormholes. While this remains highly speculative, it opens up new avenues of thought regarding how we might one day control spacetime at the quantum level. Quantum entanglement has been experimentally verified, though the mechanics behind how it works remain mysterious. If wormholes are indeed involved, they might provide a physical explanation for how entangled particles maintain their instantaneous connection, even when separated by great distances. This connection between entanglement and wormholes also brings up questions about the nature of reality. If particles can be linked through tiny wormholes, it might suggest that space and time are more interconnected than we realize, with hidden pathways that influence quantum events. Additionally, understanding this link could help physicists resolve some of the puzzles in quantum mechanics, such as the apparent contradiction between the behavior of particles at the quantum scale and the rules of classical physics. Wormholes might serve as a bridge between these two worlds. If entanglement is truly linked to wormholes, it could revolutionize our understanding of quantum communication. Technologies based on this principle might one day use these connections to send information across space instantaneously, though such applications remain theoretical for now. Quantum computers, which rely on entanglement to process information at incredibly fast speeds, could also be influenced by this connection. If wormholes play a role in entanglement, it could lead to advances in quantum computing, unlocking even greater potential for these systems. Moreover, if wormholes and entanglement are related, it might lead to breakthroughs in quantum teleportation. While we can already teleport quantum states, understanding the wormhole connection could make the process more efficient, or open up new methods of transporting information or matter. This theory also brings us closer to bridging the gap between quantum mechanics and general relativity. Wormholes exist within the framework of general relativity, while entanglement is a purely quantum phenomenon. If they are connected, it might point the way to a unified theory of quantum gravity. Ultimately, the connection between quantum entanglement and wormholes remains speculative but deeply fascinating. It pushes the boundaries of our understanding of space, time, and quantum physics, suggesting that the universe might be more interconnected than we've ever imagined. The ER/EPR theory is a bold proposal that connects two fundamental ideas in physics: Einstein-Rosen bridges, or wormholes, and quantum entanglement, also known as Einstein-Podolsky-Rosen pairs. This conjecture suggests that these two phenomena, which seem unrelated at first glance, are actually deeply connected. The ER in this theory refers to the Einstein-Rosen bridge, a type of theoretical wormhole that links two points in space-time. These bridges were first proposed by Albert Einstein and Nathan Rosen in 1935 as part of their work on general relativity. The EPR part of the theory refers to the famous EPR paradox, which also originated in 1935. This paradox explores quantum entanglement, where two particles become linked in such a way that the state of one affects the state of the other, regardless of the distance between them. Juan Maldacena and Leonard Susskind proposed the ER/EPR theory as a way to connect these two seemingly unrelated concepts. They suggested that quantum entanglement could be explained through the existence of tiny wormholes, or Einstein-Rosen bridges, linking the entangled particles. In this framework, when two particles become entangled, it's as though a microscopic wormhole forms between them, connecting their states instantaneously across space. This connection would make quantum entanglement and wormholes different expressions of the same fundamental phenomenon. This idea could help resolve some of the mysteries of quantum entanglement, particularly how particles can influence each other across vast distances without violating the speed of light. If wormholes are involved, they could act as a shortcut through spacetime, allowing for this instant communication. Although the ER/EPR theory is still speculative, it offers a potential bridge between the worlds of quantum mechanics and general relativity. Quantum mechanics governs the behavior of particles on extremely small scales, while general relativity describes the large-scale structure of the universe. EPR suggests these two realms might be linked in ways we don't yet fully understand. One of the most intriguing aspects of this theory is that it points toward a possible unification of physics. If quantum entanglement and wormholes are related, it could provide a stepping stone toward the long-sought theory of quantum gravity, which aims to unite general relativity and quantum mechanics. The EPR theory also raises interesting questions about the nature of spacetime itself. If entanglement is fundamentally linked to wormholes, then spacetime might be far more interconnected and complex than we currently imagine. This could mean that wormholes, even tiny ones, are an inherent part of the fabric of reality. If this theory holds true, it suggests that every instance of quantum entanglement could involve the creation of a microscopic wormhole. These wormholes would be far too small to be traversed by any object, but they could still serve as a kind of bridge for information between particles. The EPR theory also offers a new way to think about black holes and information. One of the biggest puzzles in theoretical physics is the information paradox, which asks whether information that falls into a black hole is lost forever. If black holes and entanglement are related through non-EPR, it might provide new insights into how information behaves in extreme conditions. Some physicists believe that EPR could help explain why quantum entanglement is such a robust phenomenon, persisting even across vast distances. If wormholes are involved, they would create a stable, though invisible, connection that maintains the entangled state regardless of distance. The EPR theory has not yet been proven, but it has inspired new ways of thinking about the relationship between quantum mechanics and spacetime. It suggests that the quantum world might be more deeply tied to the structure of the universe than. The EPR theory has profound implications for quantum gravity, which seeks to unify the principles of quantum mechanics and general relativity. If quantum entanglement and wormholes are truly connected, it could offer a new approach to solving one of the most significant challenges in modern physics. Quantum mechanics deals with the behavior of particles at incredibly small scales, while general relativity explains gravity and the large-scale structure of the universe. The two theories operate in different realms, but EPR suggests they may be connected through the fabric of spacetime itself. If wormholes exist as part of quantum entanglement, it would imply that spacetime is not smooth and continuous, as general relativity suggests. Instead, spacetime may have a complex underlying structure at the quantum level, filled with tiny connections that link particles across vast distances. This could mean that quantum gravity is not just about unifying gravity with the other fundamental forces, but about understanding how the very fabric of the universe behaves at the smallest scales. Wormholes, if tied to entanglement, may represent the fundamental building blocks of this structure. One of the most promising aspects of EPR is that it could help resolve the paradoxes that arise when trying to combine quantum mechanics and gravity. By linking the two through wormholes, physicists might develop a consistent framework that works across both quantum and cosmic scales. If spacetime itself is woven together by entanglement and wormholes, then quantum gravity would need to account for these connections. Understanding how these microscopic wormholes function could reveal new insights into the true nature of gravity at the quantum level. EPR also has implications for the nature of black holes. If the interior of a black hole is connected to the outside world through quantum entanglement, this could provide clues to solving the black hole information paradox, a major unsolved problem in theoretical physics. In this context, quantum gravity might not only describe how gravity works in extreme environments like black holes, but also explain how information escapes from them. Wormholes could offer a pathway for this information, preserving it even as it seemingly disappears into the black hole. Furthermore, this theory could redefine how we think about spacetime itself. Instead of being a static backdrop, spacetime might be dynamic and interconnected, with entanglement playing a key role in its structure. This could fundamentally change our understanding of how the universe operates at both the quantum and cosmic levels. The implications for quantum field theory are also significant. If entanglement is linked to wormholes, it might suggest that quantum fields are not confined to specific regions of space, but can interact across vast distances, connected through these hidden space-time bridges. For quantum gravity to succeed, it must bridge the gap between the smooth geometry of general relativity and the probabilistic, fluctuating nature of quantum mechanics. EPR could be a crucial step in achieving this, providing a new framework for understanding the quantum structure of spacetime. This theory also points toward a more holographic view of the universe. Some physicists propose that information about the three-dimensional universe might be encoded on two-dimensional surfaces, such as the event horizons of black holes, and EPR could provide the mechanism for this encoding through entanglement and wormholes. Additionally, EPR offers a potential explanation for the fabric of quantum space-time, suggesting that quantum gravity might emerge from entanglement itself. If so, the very nature of space-time could be a byproduct of quantum connections, reshaping our understanding of what space and time really are. Ultimately, EPR could lead to a more complete theory of everything, unifying the forces of nature under a single framework that accounts for both quantum mechanics and general relativity. It's a bold step toward understanding the deepest mysteries of the universe. If proven correct, the implications for physics would be revolutionary, offering new tools to explore everything from black holes to the origins of the universe and even the nature of reality itself. This theory could be the key to unlocking quantum gravity and understanding the true nature of space-time. Wormholes, if they exist, could play a crucial role in understanding the structure of the universe. They would not just be theoretical shortcuts through space-time, but might reveal deeper connections between different regions of the cosmos that are hidden from our view. The existence of wormholes would suggest that the universe is far more interconnected than previously thought. Space-time might not be a continuous fabric, but one filled with tunnels that link distant parts of the universe, forming a complex web of connections. And these connections could mean that regions of the universe that seem far apart from each other in normal space are actually much closer when viewed through the lens of wormholes. This would dramatically change our perception of the distances between galaxies and other cosmic structures. If wormholes are naturally occurring phenomena, they might have played a significant role in shaping the large-scale structure of the universe. The movement of matter and energy through these shortcuts could influence the formation of galaxies, stars, and other cosmic bodies. Wormholes might also explain some of the mysteries of dark matter and dark energy. If these unseen forces are connected through wormholes, it could help account for the strange gravitational effects we observe in the universe, effects that don't match up with the amount of visible matter. Another possibility is that wormholes could connect different universes in a multiverse scenario. If the universe is just one of many, wormholes might act as portals between these parallel worlds, offering a way to travel between entirely different realities. The idea that wormholes could link different parts of the universe also raises questions about causality. If information or matter can pass through a wormhole instantaneously, it might affect the fundamental nature of cause and effect in the universe. Wormholes could also provide a way to explore regions of the universe that are otherwise inaccessible. If a wormhole could connect us to a distant galaxy or even another part of the same galaxy, it could revolutionize our ability to explore and understand the cosmos. This concept challenges the conventional idea that space is flat or only curved by massive objects like stars and planets. If wormholes are part of the universe's structure, space-time might be far more dynamic, with constant shifts and connections occurring across vast distances. Some scientists suggest that wormholes might have existed since the birth of the universe, forming during the initial expansion of space-time. These primordial wormholes, if they still exist, could contain vital clues about the early universe and the forces that shaped it. The possibility of wormholes also invites speculation about the future of space travel. If we could harness these cosmic shortcuts, interstellar travel might become a reality, allowing us to visit distant star systems without the need for faster-than-light technology. Wormholes might not just be tools for travel, but also windows into the very nature of space and time. By studying them, we could learn more about the underlying structure of the universe and how different regions of space are interconnected in ways we never imagined. In a universe filled with wormholes, the concept of distance becomes fluid. What seems like an insurmountable stretch of space could be reduced to a brief passage through a wormhole, completely changing our understanding of cosmic distances and the shape of the universe. If wormholes are part of the universe's structure, they could also influence the flow of time. Wormholes that connect different points in time as well as space would challenge our current understanding of how time operates, raising questions about the possibility of time travel. Ultimately, wormholes offer a glimpse into a universe that is more complex and interconnected than we've ever imagined. Whether they are natural features of space-time or remnants of the universe's earliest moments, their discovery could revolutionize our understanding of the cosmos. Wormholes have been proposed as a potential explanation for the Big Bang, the event that marked the beginning of our universe. Some theories suggest that the universe could have emerged from a wormhole connecting our space-time to another universe or another region of space. In this scenario, the Big Bang wasn't the beginning of everything, but rather the moment when our universe exited a wormhole from a pre-existing universe. This would mean that the Big Bang was not an isolated event, but part of a larger cosmic structure that links different universes through wormholes. If wormholes are responsible for the birth of our universe, it could explain how all the matter, energy, and space-time suddenly appeared from a single point. The wormhole might have acted as a funnel, channeling everything from another universe into ours. This theory could also help explain the rapid expansion of the universe right after the Big Bang, known as cosmic inflation. If the universe emerged from a wormhole, the intense energy of that process could have driven the early inflation, pushing space to expand at an incredible rate. Additionally, the connection to another universe through a wormhole could offer an answer to the question of what came before the Big Bang. Rather than the universe emerging from a singularity with infinite density, it might have come through a wormhole from a different space-time with its own history. The idea that the Big Bang could be linked to a wormhole challenges the traditional notion that time and space began with the Big Bang. Instead, time could have existed in a different form on the other side of the wormhole, making the Big Bang an event within a much larger cosmic cycle. This theory also offers an intriguing solution to the problem of singularities, which arise in traditional models of the Big Bang. A wormhole could bypass the need for a singularity, allowing the universe to form without the infinite densities and breakdowns in the laws of physics that singularities create. If the Big Bang was caused by a wormhole, it might also explain why the universe appears so uniform on large scales. The smoothness of the cosmic microwave background radiation, for example, could be a result of the universe emerging through a wormhole from a region of space with similar properties. The idea of a wormhole linking universes also ties into the multiverse theory. If wormholes connect different universes, it's possible that the Big Bang was just one instance of a universe being created, with countless others existing alongside ours, each linked by these cosmic bridges. Wormholes could also account for the mysterious missing mass and energy of the universe, known as dark matter and dark energy. If the universe emerged from a wormhole, it might still be connected to another region of space or another universe, with matter and energy flowing between them. The idea that wormholes played a role in the Big Bang could even shed light on the arrow of time, the concept that time seems to move in one direction. If our universe emerged from a wormhole, the flow of time might be tied to the conditions on the other side, setting the stage for time to move forward after the Big Bang. This theory also opens the door to the possibility that our universe could end in a similar way. Just as it might have emerged from a wormhole, it's conceivable that the universe could one day collapse into another wormhole, creating the conditions for a new universe to form elsewhere. The notion of wormholes being responsible for the Big Bang remains highly speculative, but it offers an alternative to traditional cosmological models. By linking our universe to others through wormholes, it challenges the idea that the Big Bang was a singular event with no prior cause. If wormholes do explain the Big Bang, it would mean that our universe is part of a much larger cosmic network, where the formation and destruction of universes are regular events, all connected through these mysterious tunnels in space-time. Ultimately, wormholes as an explanation for the Big Bang would revolutionize our understanding of the origin and fate of the universe. It suggests that what we consider the beginning may just be one point in an infinite interconnected web of cosmic events. The connection between wormholes and dark matter is an area of ongoing speculation and intrigue. Dark matter, which makes up most of the universe's mass, is invisible and only detectable through its gravitational effects. Some physicists propose that wormholes could be a hidden part of this mysterious substance, One possibility is that dark matter might exist inside or around wormholes. If wormholes are scattered throughout the universe, they could influence the gravitational fields we observe, creating effects that we attribute to dark matter. This could help explain why dark matter is detectable through gravity, but remains invisible in other ways. If wormholes are connected to dark matter, it might mean that the dark matter we observe is not composed of particles at all, but is instead a manifestation of these hidden space-time structures. Wormholes could be responsible for the gravitational pull that we currently cannot account for with visible matter. Wormholes could also act as bridges connecting different parts of space, and dark matter might flow through these connections. If dark matter is moving between distant regions of the universe via wormholes, it could explain why dark matter appears to be evenly distributed across galaxies. Some theorists suggest that dark matter might actually be concentrated within the throats of wormholes. This would explain why dark matter has such a strong gravitational influence without interacting with normal matter in any other detectable way. Dark matter's elusive nature raises the question of whether it could be linked to the hidden ends of wormholes. These ends might be located in other dimensions or regions of the universe that we cannot directly observe. If dark matter is connected to these unseen regions, wormholes could serve as a conduit between them and our observable universe. Another possibility is that wormholes and dark matter are both consequences of the same underlying structure of the universe. If spacetime is filled with wormholes, they might create gravitational effects that we interpret as dark matter, even though the true source of these effects is the wormholes themselves. If wormholes are connected to dark matter, it could also help explain the behavior of dark matter in galaxy formation. Dark matter is known to play a crucial role in holding galaxies together, and wormholes could influence this process by providing hidden gravitational pathways that affect the movement of matter. The idea that wormholes and dark matter are linked also opens up new possibilities for understanding dark energy, the mysterious force driving the accelerated expansion of the universe. If wormholes are part of the structure of dark matter, they could be connected to the mechanisms that cause the universe to expand at an ever-increasing rate. If dark matter is associated with wormholes, it might also explain why dark matter interacts so weakly with ordinary matter. The matter passing through wormholes could be inaccessible to us because it is trapped in the wormhole's throat or flowing between different regions of spacetime, out of reach of our instruments. This theory could provide new insights into why dark matter behaves differently from regular matter. If wormholes are involved, the gravitational influence of dark matter might come from the distortions in spacetime that the wormholes create, rather than from dark matter particles interacting with ordinary matter. Some researchers suggest that dark matter could even be matter from other universes passing through wormholes into our universe. In this scenario, wormholes might act as gateways, allowing matter to move between different regions of a multiverse, creating the gravitational effects we observe. The potential connection between wormholes and dark matter offers an intriguing explanation for why dark matter is so difficult to detect directly. If dark matter is tied to wormholes, it might exist in a form that is fundamentally different from the particles we are trying to find in laboratory experiments. If proven, this connection could lead to a breakthrough in our understanding of both dark matter and wormholes. It would mean that the universe is filled with hidden structures that not only explain the behavior of dark matter, but also offer new possibilities for travel, communication, and exploration through space-time. Ultimately, exploring the link between wormholes and dark matter could provide the key to solving some of the biggest mysteries in cosmology. It could reveal A. Wormholes in the multiverse theory suggest that these tunnels through space-time could connect not just different regions of our universe, but entirely separate universes. If the multiverse exists, wormholes might act as bridges between parallel worlds, offering a means of traveling from one universe to another. In this scenario, each universe in the multiverse could have its own unique laws of physics, and wormholes might allow passage between them, creating the possibility of exploring these alternate realities. However, the conditions within these wormholes would be extreme, and survival might depend on the specific physics of the destination universe. The multiverse theory proposes that there are countless other universes beyond our own, each possibly existing in a different dimension or following its own distinct rules of nature. Wormholes could serve as the only link between these otherwise disconnected realms, offering a way to access these parallel worlds. If wormholes can connect different universes, it raises the possibility that certain physical constants, like the speed of light or the force of gravity, might be different on the other side. Traveling through a wormhole could mean entering a universe where the fundamental nature of reality has shifted. Some scientists suggest that wormholes in the multiverse theory could explain some of the unusual phenomena we observe in our universe. Certain cosmic anomalies or unexplained gravitational effects might result from the influence of another universe connected to ours through a hidden wormhole. In this context, wormholes might also offer a solution to the mystery of why our universe appears so fine-tuned for life. If countless universes exist, each with different properties, it's possible that only certain universes, like ours, have the right conditions to support life. Wormholes could allow us to glimpse or even access these other universes. The concept of wormholes linking multiple universes also ties into ideas of cosmic inflation, where the early universe expanded rapidly. Wormholes might have formed during this period, creating permanent connections between universes that were born from the same initial conditions but evolved differently. If wormholes exist in the multiverse, they could potentially provide a way to communicate between universes, even if physical travel is impossible. Signals or particles might pass through these wormholes, allowing for the exchange of information between otherwise isolated worlds. Another fascinating possibility is that our universe could have originated from a wormhole. If our universe emerged from a larger multiverse, a wormhole might have funneled the energy needed to create the Big Bang, suggesting that wormholes played a role in the formation of entire universes. Wormholes in the multiverse theory also challenge our understanding of time. In some models, time might flow differently in parallel universes, and traveling through a wormhole could lead to strange effects, such as emerging in a universe where time has progressed at a different rate. This theory also raises the possibility of universes that are vastly different from our own. While some might resemble ours, others could have completely different physical laws, making them uninhabitable or even incomprehensible. Wormholes could be the only way to explore these diverse universes without leaving our own. If wormholes link different universes, they could also offer an explanation for the mysterious concept of quantum entanglement. It's possible that entangled particles in our universe are actually connected through a wormhole to particles in another universe, suggesting that the multiverse plays a role in quantum mechanics. The existence of wormholes in the multiverse might also help explain dark energy and the accelerated expansion of our universe. Energy could flow between universes through wormholes, influencing the rate of expansion and the behavior of galaxies over time. These interuniversal wormholes could also provide a solution to the information paradox associated with black holes. If information that falls into a black hole can pass through a wormhole to another universe, it might resolve the question of whether information is truly lost. Ultimately, the idea of wormholes in the multiverse theory pushes the boundaries of our understanding of the cosmos. It opens up new possibilities for exploration, discovery, and understanding of not just our universe, but the countless other worlds that may exist beyond it. Wormholes could, in theory, connect parallel universes, offering a bridge between realms that otherwise exist independently of each other. These connections might allow for travel or communication between universes, providing a way to explore alternate realities beyond our own. If parallel universes exist, each one could have its own distinct version of spacetime. A wormhole might create a tunnel that bypasses the boundaries of one universe and leads into another, essentially linking two separate dimensions together. Some models suggest that these wormholes could be stable, allowing for continuous interaction between universes. However, the stability of such a connection would likely depend on the properties of both universes, meaning the wormhole could collapse if the conditions on either side change. Traveling through a wormhole to a parallel universe might mean encountering entirely different laws of physics. Gravity, time, and even the basic forces that govern matter might function differently, creating an alien environment that is unpredictable and potentially dangerous. Wormholes could also provide a way to explain the existence of parallel universes without them being completely inaccessible. If wormholes exist, they might not only connect regions within our universe, but also serve as gateways between entirely separate universes, offering a new perspective on the multiverse. The connection between wormholes and parallel universes challenges the idea of isolation between dimensions. If wormholes can link these universes, it suggests that they are not entirely closed off from one another, but may be part of a larger, interconnected system of realities. One intriguing possibility is that these wormholes could allow matter or energy to flow between universes. This could explain some of the anomalies we observe in our own universe, as energy from a parallel universe might occasionally seep through a wormhole, influencing our reality. If wormholes connect parallel universes, they might also offer a solution to some of the most puzzling aspects of quantum mechanics. The behavior of entangled particles, for example, could be explained if those particles are linked by wormholes that pass through different universes. Such connections would also raise questions about the nature of time. In some parallel universes, time might flow at a different rate, or even move in reverse. Entering a wormhole could mean traveling not just to another universe, but to another timeline entirely, where past and future take on new meanings. Wormholes might also serve as a way to explain how universes in a multiverse could interact. If these universes are connected by wormholes, it suggests that they are not completely independent, but are instead part of a broader cosmic structure, where interactions, though rare, are possible. If humans ever find a way to traverse wormholes, reaching a parallel universe might become more than just a theoretical concept. However, the differences between universes could make it incredibly difficult to survive or even comprehend the conditions on the other side. Wormholes linking parallel universes could also provide answers to why our universe appears so finely tuned for life. If countless other universes exist with different physical properties, wormholes could be the key to exploring these alternate realities and understanding why ours is the way it is. The idea of wormholes connecting parallel universes also sparks questions about causality. If events in one universe can influence another through a wormhole, the chain of cause and effect could be altered, potentially leading to paradoxes that challenge our understanding of time and space. These wormholes might even allow for the transfer of information between universes, creating the possibility of communicating with intelligent life forms in alternate dimensions. This would open up an entirely new realm of exploration and discovery beyond the limits of our own universe. Ultimately, wormholes connecting parallel universes represent one of the most fascinating possibilities in modern physics. If they exist, they could fundamentally change our understanding of the universe, offering new ways to explore not just our own reality but countless others beyond it. Despite the intriguing theories surrounding wormholes, there is currently a complete lack of experimental evidence to support their existence. Everything we know about them is derived from theoretical physics, particularly from solutions to Einstein's equations of general relativity. No telescope has observed a wormhole, and no experiment has detected any physical effects that could be attributed to one. Wormholes remain speculative because, so far, all attempts to find direct or indirect evidence have come up empty. One reason for this lack of evidence is that if wormholes do exist, they might be incredibly difficult to detect. They could be hidden deep within galaxies or existing on scales too small for us to observe, making them effectively invisible to our current instruments. Another challenge is that wormholes might require exotic matter with negative energy to remain stable, something we have never observed in the universe. Without such matter, even if wormholes do exist, they would likely collapse before we could detect them. Even though black holes have been directly observed, there is no sign that any of them serve as entrances to wormholes. If wormholes were connected to black holes, we would expect to see unusual effects, but so far none have been found. Gravitational waves, ripples in spacetime caused by massive cosmic events, could provide a clue. However, the waves we've detected from black hole collisions match what we expect from general relativity, showing no signs of being linked to wormholes. Some scientists have suggested that wormholes could be detected through gravitational lensing, where light bends around a massive object. But the bending caused by a wormhole would likely look similar to the effect of a black hole, making it nearly impossible to tell the difference. Quantum experiments have also failed to provide any evidence for wormholes. While quantum entanglement and other phenomena are mysterious, there's no solid data that directly links these effects to wormholes, leaving the connection speculative. It's possible that wormholes could exist at the quantum scale, far too small for us to observe. If this is the case, Detecting them would require a breakthrough in technology that allows us to probe deeper into the structure of spacetime. Another reason for the lack of evidence might be that wormholes, if they exist, are extremely rare. If only a handful of them exist across the vast universe, our chances of stumbling upon one would be incredibly slim with our current observational tools. Wormholes might also be unstable by nature, collapsing so quickly that they don't last long enough to be detected. This would make capturing direct evidence nearly impossible, as the phenomena would vanish before our instruments could pick up any signals. Even though no evidence exists, scientists continue to search for signs of wormholes, hoping that future experiments or advanced technologies might one day reveal them. Until then, wormholes remain purely hypothetical constructs in the world of theoretical physics. Some researchers are optimistic that with the development of more powerful telescopes or gravitational wave detectors, we might eventually observe anomalies that could point to the existence of wormholes. However, this remains speculative at best. The absence of evidence doesn't necessarily mean wormholes don't exist, but it highlights how far we are from understanding them. Without experimental verification, wormholes remain a fascinating but elusive idea that challenges our understanding of space-time. For now, the lack of experimental evidence keeps wormholes in the realm of theory. While their potential is exciting, we must be cautious in drawing conclusions until solid, observable data emerges to either confirm or refute their existence. One of the biggest problems with exotic matter is that it has never been observed in nature. Exotic matter, with its negative energy density, is a crucial requirement for keeping a wormhole stable, but we have no direct evidence that it exists in the quantities necessary to support a traversable wormhole. Theoretical physics suggests that exotic matter could be created under very specific conditions, like in the Casimir effect, where negative energy appears between two closely spaced plates. But the amount of negative energy generated in such scenarios is incredibly small, nowhere near enough to stabilize a wormhole. Even if exotic matter could be created, controlling it would be another enormous challenge. Negative energy might behave unpredictably, and harnessing it would require advanced technologies far beyond anything we currently possess. Another issue is the potential instability of exotic matter. Negative energy might not be easy to maintain, and any fluctuation in its properties could cause the wormhole to collapse, trapping or destroying anything inside it. Exotic matter could also raise concerns about violating certain physical laws, like the conservation of energy. Traditional physics holds that energy cannot be created or destroyed, but exotic matter's negative energy properties might conflict with these fundamental principles. Some physicists speculate that exotic matter could only exist in extreme environments, like the interiors of black holes or during the early moments of the universe's formation. If that's the case, accessing or producing exotic matter in a laboratory setting would be nearly impossible. Furthermore, exotic matter might have unusual interactions with ordinary matter. The repulsive gravitational forces generated by exotic matter could have unpredictable effects on anything attempting to pass through a wormhole, potentially making safe travel difficult. There's also the question of whether exotic matter could be synthesized artificially. Even if quantum effects suggest its existence, creating and stabilizing large amounts of it would require energy and resources beyond our current technological capabilities. Another potential problem is that exotic matter could have dangerous consequences if it interacts with the surrounding spacetime in unexpected ways. Uncontrolled negative energy could distort spacetime, leading to unpredictable gravitational effects that could destabilize the wormhole. In addition to the technical challenges, there are ethical concerns about experimenting with exotic matter. Manipulating spacetime and negative energy on large scales could pose unforeseen risks, not just to the immediate environment, but potentially to the entire structure of the universe. Even theoretical models struggle with the complexities of exotic matter. While general relativity allows for the possibility of negative energy, combining it with the quantum mechanical requirements for creating a stable wormhole presents mathematical difficulties that remain unresolved. Another complication is that the amount of exotic matter required might be astronomically large. Some estimates suggest that stabilizing a macroscopic wormhole could require more exotic matter than exists in the observable universe, making the concept far less practical. If exotic matter does exist, it could be incredibly rare, scattered across the universe in quantities too small to detect. This scarcity makes it difficult to study or experiment with, limiting our understanding of how it might function in the context of wormholes. The presence of exotic matter could also disrupt local gravitational fields in unexpected ways. If we ever attempt to create a wormhole using exotic matter, it might have unintended consequences on nearby celestial bodies, causing gravitational anomalies. Ultimately, the problems with exotic matter remain a significant barrier to the practical realization of traversable wormholes. Without a way to find, create, or control it, the concept of stable wormholes will remain confined to theoretical discussions rather than practical application. Wormhole stability is one of the most critical challenges in making them traversable. Without a way to keep a wormhole stable, it would collapse almost immediately after forming, making it impossible to pass through. The immense gravitational forces involved would cause the tunnel to close before anything could travel across. One of the reasons wormholes are so unstable is due to the natural curvature of spacetime. Under normal circumstances, spacetime tends to collapse in on itself when bent too far, and the mouth of a wormhole would need to be held open against this pressure. In theory, exotic matter could provide the repulsive force needed to stabilize the wormhole's throat, preventing it from collapsing. But as mentioned earlier, exotic matter is purely theoretical and has yet to be discovered or produced in the necessary quantities. Even if exotic matter could be found, distributing it evenly around the wormhole's throat would be a massive challenge. Any imbalance in the placement of exotic matter could result in the wormhole collapsing or distorting, making it unsafe for travel. Another issue with stability is that wormholes may be subject to tidal forces, similar to the effects near a black hole. These forces could stretch and compress anything entering the wormhole, potentially destroying the structure or anything trying to pass through. Additionally, wormholes might be sensitive to external disturbances. Cosmic radiation, gravitational waves, or even nearby matter could disrupt the delicate balance, keeping the wormhole open, leading to its sudden collapse. Wormhole stability may also depend on the scale of the wormhole itself. Smaller, microscopic wormholes might be more inherently unstable, flickering in and out of existence too quickly for us to observe or use, while larger wormholes would require far more exotic matter to remain open. Another challenge is ensuring that both ends of the wormhole remain stable and connected. If one mouth shifts or moves due to gravitational forces or space-time distortions, the entire wormhole could unravel, leaving travelers stranded or worse. Time dilation effects near the wormhole could further complicate its stability. The closer you get to a wormhole's throat, the more time would appear to slow down due to the intense gravitational fields, and this uneven flow of time might add to the instability. There's also the possibility that wormholes, even if stabilized, could gradually degrade over time. Small fluctuations in the energy levels or space-time curvature might accumulate, eventually leading to the collapse of the wormhole after prolonged use. The creation of a stable wormhole might require constant input of energy or exotic matter. This means that maintaining a wormhole could be an ongoing process, with any lapse in energy supply causing the entire structure to collapse instantaneously. Additionally, wormholes might suffer from feedback loops, where small disruptions get amplified over time. These feedback loops could accelerate the collapse of the wormhole, making it incredibly difficult to maintain stability for any significant period. Even if a wormhole could be stabilized for a short time, it might not stay open long enough for safe passage. If the wormhole begins to collapse while a traveler is inside, the forces involved could trap or destroy them before they reach the other side. Wormholes could also be unstable if connected to regions of space-time with different physical properties. If the ends of a wormhole connect areas with vastly different gravitational fields or energy levels, it could create additional stresses on the wormhole's structure. Ultimately, the stability issues surrounding wormholes present one of the biggest hurdles to making them usable for travel. Without a reliable way to prevent collapse and ensure that the wormhole remains open and stable, they will remain more of a theoretical curiosity than a practical tool for exploration. Many leading physicists remain skeptical about the existence and practicality of wormholes. One of the primary critiques is that while wormholes are mathematically possible within the framework of general relativity, there is no experimental evidence to support their existence. Without observational proof, they remain speculative. Stephen Hawking was particularly critical of the idea of wormholes as time machines. He proposed the chronology protection conjecture, suggesting that the laws of physics might prevent time travel through wormholes to avoid paradoxes, effectively making traversable wormholes impossible. Hawking also believed that even if wormholes could form, they would likely be highly unstable. The energy needed to stabilize a wormhole would be so great that any attempt to use it for travel could cause it to collapse almost instantly, destroying anything inside. Kip Thorne, one of the most prominent physicists studying wormholes, acknowledges the theoretical possibility, but also emphasizes the extreme challenges. He highlights that while exotic matter could stabilize a wormhole, creating or finding such matter is far beyond our current technological capabilities. Roger Penrose has also expressed skepticism. He believes that the extreme conditions required to maintain a stable wormhole, such as the use of negative energy, are unlikely to occur naturally, making the existence of traversable wormholes highly improbable in the real universe. Another critique comes from Leonard Susskind, who questions whether wormholes would ever be practically useful for travel. He suggests that even if they exist, the time it would take to navigate and stabilize a wormhole might negate any advantages over traditional space travel. Carlo Rovelli has pointed out that wormholes, while fascinating, are distractions from more pressing problems in physics. He argues that the energy and effort spent on speculative theories about wormholes might be better used in exploring quantum gravity and understanding black holes. Lisa Randall, a theoretical physicist, has also raised concerns about the practical limitations of wormholes. She notes that even if they exist, wormholes would likely be so small or fleeting that they wouldn't be useful for human travel or communication. Physicist Sean Carroll echoes these doubts, stating that while wormholes are mathematically intriguing, they require assumptions about exotic matter and energy that don't align with anything we've observed in the universe. He stresses the importance of grounding speculation in observable phenomena. Brian Greene, known for his work on string theory, remains open to the idea of wormholes but also emphasizes the difficulty of finding experimental evidence. He suggests that even if wormholes exist, detecting them would require an unprecedented leap in our observational technology. Neil deGrasse Tyson often discusses the limits of our understanding when it comes to wormholes. He points out that while they are fun to theorize about, we have no reliable data to suggest they are anything more than mathematical constructs at this point. Physicist Sabine Hossenfelder is particularly critical of the way wormholes are often sensationalized in popular science. She argues that while they are mathematically interesting, the focus on wormholes can detract from more grounded scientific inquiry into the nature of spacetime. Michio Kaku, while more optimistic about future possibilities, acknowledges that the obstacles to creating a stable wormhole are immense. He often discusses how wormholes could theoretically work, but agrees that making them a reality is beyond our current reach. Edward Witten, one of the pioneers of string theory, has expressed doubt about the stability of wormholes within the framework of quantum mechanics. He argues that the quantum effects required to stabilize a wormhole might not be possible in the real world. In the end, the critiques from these leading physicists highlight the enormous gap between theoretical models and practical reality. While wormholes remain an intriguing idea, the lack of evidence and the many unresolved challenges keep them firmly in the realm of speculation for now. Advancements in space-time manipulation are still in their early stages, but researchers are exploring ways to better understand and possibly control the fabric of space-time. One of the most significant areas of study is the concept of bending space-time, as described by Einstein's theory of general relativity. In recent years, the detection of gravitational waves has opened a new window into how space-time can be distorted by massive objects. These waves demonstrate that space-time is not fixed, but can ripple, stretch, and compress under the right conditions. This discovery has inspired further research into whether these effects can be harnessed or replicated. Some scientists are investigating how to manipulate gravitational fields artificially. If we could control gravity on a large scale, it might offer insights into bending space-time in specific ways, potentially creating conditions similar to those required for a wormhole or other advanced space-time phenomena. Quantum mechanics also plays a significant role in space-time manipulation. Quantum entanglement and other quantum effects suggest that space-time may have properties that we don't yet fully understand. By studying these effects, physicists hope to uncover new methods for interacting with the very structure of the universe. Advancements in technologies like particle accelerators are contributing to our understanding of spacetime at the smallest scales. By recreating conditions that existed just after the Big Bang, researchers can observe how spacetime behaves under extreme conditions, offering clues about how to manipulate it. There is also ongoing research into the potential of negative energy and exotic matter, which could theoretically be used to warp spacetime. While we haven't yet discovered these materials in usable quantities, understanding their properties could be a breakthrough in spacetime manipulation. Another area of interest is the Casimir effect, where tiny amounts of negative energy are generated between closely spaced objects. This effect shows that under the right conditions, spacetime can be influenced on small scales, suggesting that similar principles could be applied on a larger scale. Some physicists are working on models that explore how spacetime could be folded or warped to create shortcuts through the universe, akin to wormholes. These models remain speculative, but they provide a foundation for future research into how spacetime might be manipulated for practical purposes. Researchers are also exploring the possibility of using high-energy laser systems to create local distortions in spacetime. While this idea is still largely theoretical, advancements in laser technology could one day provide a means of testing these concepts in the lab. The field of quantum gravity, which seeks to unify general relativity with quantum mechanics, is another promising area for spacetime manipulation. If scientists can develop a theory of quantum gravity, it could reveal entirely new ways of interacting with spacetime on both large and small scales. Some experiments are even examining the possibility of teleportation using quantum entanglement. Although this doesn't involve direct manipulation of spacetime, it hints at how quantum processes might one day allow us to bypass traditional concepts of distance. Advances in supercomputing are helping scientists simulate how spacetime behaves under various conditions. These simulations are crucial for testing the feasibility of spacetime manipulation theories without needing to recreate the conditions of the early universe. Space agencies like NASA are also interested in the potential for manipulating spacetime, particularly for long-distance space travel. While still in its infancy, the idea of bending spacetime to create faster-than-light travel is a topic of active discussion in theoretical circles. Recent breakthroughs in understanding black holes have also shed light on how spacetime can be stretched and compressed. By studying the intense gravitational fields near black holes, scientists hope to learn more about how to control similar forces on smaller scales. Ultimately, while spacetime manipulation remains a distant goal, advancements in quantum mechanics, gravitational studies, and high-energy physics are steadily pushing the boundaries of what we know. These efforts are laying the groundwork for future breakthroughs that could make the dream of controlling spacetime a reality. Scientists are constantly exploring potential experiments that could either detect existing wormholes or even create them under the right conditions. One of the primary methods being discussed involves the use of high-energy particle collisions. By smashing particles together at extreme speeds, researchers hope to recreate conditions similar to those just after the Big Bang, when spacetime might have been more flexible, potentially leading to the creation of tiny, short-lived wormholes. Gravitational wave detectors like LIGO and Virgo have already proven their ability to detect ripples in spacetime caused by massive objects like black holes. If a wormhole were to exist, passing objects or energy through it could create unique gravitational wave patterns, allowing us to detect their presence indirectly. Physicists are also looking at gravitational lensing, where light bends around a massive object due to its gravitational field. If a wormhole were to exist between two regions of space, it could create unusual lensing effects that don't align with what we typically observe around black holes. Another potential experiment would involve detecting exotic matter or negative energy. If wormholes require exotic matter to remain stable, then finding traces of this matter would provide a significant clue. Some researchers propose using quantum field experiments to detect the presence of negative energy in the vacuum of space. There's also interest in using particle accelerators to search for microscopic wormholes. These would be far too small to allow for human travel, but their detection would still confirm the theoretical basis of wormholes. By closely analyzing particle collisions, researchers might detect anomalies that hint at wormhole formation. Quantum entanglement offers another avenue for experimentation. If wormholes are connected to quantum entanglement, as some theories suggest, then manipulating entangled particles in a lab could offer indirect evidence of a wormhole's presence. Observing how these particles behave under extreme conditions could provide insights into space-time structure. The Casimir effect, where negative energy is observed in a vacuum between two plates, might also be used in wormhole research. By scaling up this effect or finding ways to manipulate it, scientists could experiment with creating the type of negative energy required to keep a wormhole open. Astronomers are looking for unusual cosmic signals that might indicate the presence of a wormhole. If objects suddenly disappear or reappear in unexpected places, or if we detect energy that seems to have no source, this could suggest a wormhole is acting as a bridge between different parts of space. Another idea is to explore the extreme environments around black holes, where space-time is already heavily warped. If a wormhole could form naturally anywhere, it might be in the intense gravitational fields surrounding a black hole. Observing black holes closely with next-generation telescopes could reveal telltale signs of a wormhole connection. Some theorists suggest that large-scale cosmic structures, like galaxy clusters, could be linked by naturally occurring wormholes. Searching for subtle distortions in the gravitational fields of these clusters might provide indirect evidence of a hidden network of wormholes. Using quantum computers, physicists might also simulate wormhole behavior under various conditions. These simulations could help refine our understanding of how to detect or create a wormhole in the real world, guiding future experiments. The potential use of lasers and electromagnetic fields is another avenue being explored. High-energy lasers might be used to create tiny distortions in spacetime, which could potentially lead to the creation of micro-wormholes. While still theoretical, this approach is part of ongoing research into manipulating spacetime directly. There's also the possibility of detecting dark matter or energy anomalies. If wormholes exist, they might influence the behavior of dark matter, creating unusual gravitational effects that we could observe using new technologies designed to track the movement of dark matter particles. One of the most exciting prospects is the idea of using quantum ent. If wormholes could be stabilized and harnessed, the implications for space travel would be revolutionary. Instead of taking decades or centuries to reach distant stars, we could travel vast distances almost instantaneously by passing through a wormhole, completely transforming our approach to exploring the cosmos. This would make interstellar travel a reality within human lifetimes, allowing us to explore nearby star systems, planets, and even distant galaxies. The ability to bypass the speed of light limitation would unlock the possibility of human expansion beyond our solar system. Wormholes could also reduce the need for traditional propulsion systems. If we could create stable wormholes, spacecraft wouldn't need engines capable of long-term travel, as the journey through the wormhole would take place in a matter of moments. Travel through wormholes could also solve some of the challenges associated with long-term space missions, such as the effects of time dilation. Wormholes, by acting as shortcuts, might allow us to avoid the intense relativistic effects that come with traveling close to the speed of light. The ability to travel across vast distances would also accelerate our search for habitable planets. Instead of sending probes on decades-long journeys to other star systems, we could potentially reach these worlds within days, drastically improving our chances of finding life. It could open the door to exploration of other galaxies. In the current model of space travel, reaching even the closest galaxy, Andromeda, would take millions of years. With wormholes, this kind of exploration could become feasible within a single human generation. If wormholes could be used for transportation, they might also allow for rapid trade and communication between distant parts of the galaxy. Entire civilizations could be connected through a network of wormholes, leading to a more unified understanding of the universe. Wormholes could also serve as a new frontier for colonization. If they could be stabilized and made safe, they would offer humanity the opportunity to establish colonies on distant planets and moons without the time and resource constraints of traditional space travel. The impact on space exploration missions would be profound. Space agencies like NASA, the ESA, and private companies would no longer need to invest in long-duration missions to reach the outer planets or far-off destinations. Wormholes could make exploration of the entire universe a tangible goal. These advancements might even lead to the creation of intergalactic travel networks, connecting different star systems and galaxies with ease. The development of stable wormholes could shift space exploration from the slow, incremental progress we see today to a rapid, interconnected web of exploration. The potential for scientific research would also expand dramatically. Astronomers and physicists could directly study distant stars, black holes, and other cosmic phenomena up close, rather than relying on light-years-old data. Wormholes could offer new insights into the formation of the universe and its hidden structures. Space travel through wormholes could also eliminate the problem of radiation exposure during long space journeys. Current space travel subjects astronauts to dangerous levels of cosmic radiation, but if the trip through a wormhole only takes moments, the exposure would be minimal. Beyond exploration, wormholes could make resource extraction from distant planets and asteroids much more viable. Mining operations on distant worlds could become economically feasible if transporting materials through wormholes were quick and efficient. Finally, the implications for human survival are enormous. If Earth were ever threatened by a catastrophic event, wormholes could provide a rapid escape route to other habitable worlds, offering humanity the possibility of long-term survival in the universe. Ultimately, wormholes would change our entire perspective on space travel. Instead of being limited by the vast distances of the universe, we could start thinking of space as a navigable, interconnected system, bringing distant worlds within our reach. The prospects for real-world wormhole discoveries remain speculative, but ongoing advancements in theoretical physics and astrophysics keep the possibility alive. While no direct evidence of wormholes has been found, their existence is still considered plausible within the framework of general relativity. One of the most promising avenues for discovering wormholes lies in the study of gravitational waves. If a wormhole exists, it might produce a distinct gravitational wave signature as objects pass through it. These patterns would be different from those produced by black holes or neutron stars. Astronomers are also on the lookout for unusual gravitational lensing effects. Wormholes could bend light in ways that differ from other massive objects, creating distorted images of distant galaxies or stars. Such anomalies might provide clues about the presence of a wormhole. Detecting wormholes might also involve studying black holes more closely. Some scientists theorize that certain black holes could be entrances to wormholes. If we could observe something escaping from a black hole, or detect unusual behavior near the event horizon, it might suggest a wormhole connection. Another potential discovery method involves studying dark matter and dark energy. Since these mysterious forces dominate the universe, yet remain invisible, some scientists speculate that wormholes could be linked to them. Finding a connection between dark matter and wormholes could provide new insights into both phenomena. Quantum physics offers another avenue for exploration. Some theories suggest that wormholes might exist at the quantum level, flickering in and out of existence. If we can better understand how quantum mechanics and general relativity intersect, we might uncover evidence of micro-wormholes. The development of more sensitive telescopes and detectors could increase the chances of discovering a wormhole. Instruments like the Event Horizon Telescope, which captured the first image of a black hole, might one day capture similar evidence for a wormhole if one exists. There is also a possibility that wormholes, if they exist, are simply too far away or too rare for us to detect with current technology. Even if they're scattered across the universe, their distance and size could make them nearly impossible to find without major technological advancements. Experiments in high-energy physics, particularly those involving particle accelerators, might provide indirect evidence of wormholes. By recreating the conditions of the early universe, researchers might uncover hints of the space-time fluctuations that could give rise to wormholes. Wormhole discoveries might also be linked to breakthroughs in quantum gravity. If we can develop a unified theory that combines general relativity with quantum mechanics, it could unlock a deeper understanding of how wormholes could form and function within the universe. Artificial intelligence and machine learning could play a role in wormhole discovery as well. By analyzing vast amounts of cosmic data, AI could identify patterns or anomalies that humans might overlook, potentially leading to indirect evidence of wormholes. Theoretical physicists continue to refine their models of space-time, searching for ways to test the existence of wormholes. These models could eventually guide experiments or observations that bring us closer to confirming their reality. While the discovery of wormholes remains elusive, the concept continues to inspire new scientific inquiries. Each breakthrough in our understanding of gravity, quantum mechanics, and the structure of the universe brings us one step closer to determining whether wormholes are more than just theoretical constructs. Even if we don't discover wormholes soon, the search for them is likely to reveal new insights into the nature of spacetime. The exploration of such extreme conditions may help answer other fundamental questions about the universe's origins and the limits of our physical laws. The prospects for real-world wormhole discoveries are uncertain, but as our technology and understanding of the universe continue to evolve, the possibility remains that we may one day confirm the existence of these cosmic shortcuts. Throughout this video, we've explored the fascinating concept of wormholes, from their theoretical origins in Einstein's general relativity to their potential role in the structure of the universe. We've discussed the difference between Schwarzschild and traversable wormholes, diving into what makes them distinct, and the challenges of keeping them stable for travel. We've delved into the mathematical basis for wormholes, showing how they emerge from solutions to Einstein's field equations. We touched on the Einstein-Rosen bridge and its connection to general relativity, and how these ideas have shaped modern understanding of spacetime and wormholes. The role of exotic matter and negative energy was a major topic, highlighting the importance of these hypothetical substances in maintaining a wormhole's stability. We also discussed how quantum theory plays a part in wormhole science, offering intriguing possibilities for stabilizing and detecting these space-time shortcuts. We ventured into more speculative territory, with ideas like time travel through wormholes and closed timelike curves, exploring both the scientific potential and the paradoxes that might arise. Alongside that, we looked at the views of famous physicists on these topics, examining both their enthusiasm and skepticism. The lack of direct observational evidence remains a significant hurdle, as we discussed, yet the detection of gravitational waves offers hope that wormholes might one day be found. We also compared black holes to wormholes and explored the search for exotic matter, crucial for stabilizing these cosmic tunnels. In addition, we examined how wormholes could connect parallel universes, offering gateways to other realms in a multiverse, and considered whether wormholes might explain some of the mysteries of the Big Bang. These theories open up tantalizing possibilities about the very nature of our universe. While wormholes are often depicted in science fiction as shortcuts through space and time, we discussed how real-world science views them and the immense challenges involved in making them a reality. From the problems with exotic matter to the instability of wormholes, it's clear that we have much to learn before wormholes become more than theoretical concepts. We also covered the current efforts in wormhole research and the advancements being made in space-time manipulation. Although we're far from being able to create or detect wormholes, continued research in these areas could bring us closer to unlocking the secrets of the universe. Looking to the future, we explored the potential experiments that could one day detect or even create wormholes, as well as the implications that wormholes could have for space travel. If we ever manage to stabilize and harness these tunnels, they could transform our ability to explore distant worlds. If you enjoyed this deep dive into the science of wormholes, don't forget to like this video and subscribe to the channel for more content like this. We've got plenty of other fascinating topics on the channel, so feel free to check out our other videos on space, time, and the mysteries of the cosmos. Thanks for watching.